Let's get started. Welcome to day 3. Let me slow down this fan a little bit, it's noisy. Yeah. Okay. All right. Let's get started. This is day 3 and we are here almost halfway through our short course. So today we have three lectures and one tutorial at the end of the day. We will begin with a lecture on measurement of measurement of battery thermal properties, and then I will continue our discussion on the theoretical analysis of heat transfer. Yesterday we talked about steady state modeling. Today I will talk about transient heat transfer. And then later in the day there will be a lecture on thermal stability analysis, which will be all about prediction of whether thermal runaway will occur in a lithium ion cell or not. And finally we will continue our ANSYS simulation tutorial that I had started yesterday. Okay, any questions or comments from the attendees at this point? All right, then let's get started. So we have seen that typically lithium ion cells come in two different configurations, cylindrical and prismatic. And the theme of our short course has been to understand the nature of heat transfer in these systems, ultimately to be able to keep lithium ion cells cool enough and prevent them from getting overheated, right? It turns out from a heat transfer point of view that if you look at the equations governing heat transfer in any system, for example, for a prismatic cell, we could write something like this. Solving this differential equation gives us the temperature field of the body, right? Therefore, we can say that the temperature field in the body is a function of K, rho and Cp. These are the three properties of the cell that determines how hot it will get, right? And therefore it is very important for us to know what the values of these properties are. Okay, so long time ago when I started my work in this field, this colleague of mine walks into my office and says, we have lithium ion cells, they're getting too hot, can you predict what we can do to keep them cool? And my first question to him was, well, what is the thermal conductivity of your cell? We went to the literature and found that there really wasn't a lot of reports of the values of these thermal properties, right? And therefore we and others in the community have spent a good amount of time and effort in measuring the thermal properties of these lithium ion cells. So today we will talk about how such properties can be measured or determined in order to guide our thermal design process. Okay, K is the thermal conductivity. We saw this when we were doing our introduction to fundamental heat transfer. If you may recall, it has units of watt per meter Kelvin. Cp is the heat capacity. That has units of joules per kg Kelvin, and rho is of course the density, that has units of kg per meter cube. What is the meaning of thermal conductivity? Thermal conductivity governs the rate at which heat flows, correct? Q double prime equals negative K delta T, correct? Or rather dt dx. For the same temperature gradient, material A and material B will have different flows of heat depending on their thermal conductivities, right? So clearly, if I want to remove heat out of this cell, its thermal conductivity is of paramount importance. This thermal conductivity for the cell should be as high as possible, right? That's the meaning of thermal conductivity. The meaning of density is of course quite clear. It is the mass density, how many kilograms there are per meter cube. The meaning of heat capacity, we have also seen this. The heat capacity appears in the expression for the energy content of the body. MCPT is the amount of energy contained in the body, right? And oftentimes the heat capacity basically determines how much energy is needed to raise the temperature of the body by 1 Kelvin, 1 kilogram of the body by 1 Kelvin, right? That is the classic definition of the heat capacity. Higher the heat capacity, greater is the ability of the body to absorb heat and keep it in it without any temperature rise, right? That is the reason why cities that are close to the ocean don't get very hot in the summers, because the ocean is able to absorb a great deal of heat from the sun without any temperature rise. Whereas a city in the desert with a lot of sand has low heat capacity, and therefore the energy coming from the sun will raise the temperature of the sand very rapidly, right? In the context of lithium ion cells, we are interested in understanding what are the values of K, rho and Cp for the cells. Keep in mind also that while the heat capacity is just one single valued quantity, thermal conductivity may be anisotropic. So it is possible that I may have three different components of thermal conductivity, either kx, ky, kz, or kr, k theta, kz. In other words, for a given material, the thermal conductivity in the three directions may be different from each other, and we need to recognize that. Okay, I think it's important for us to get a feel for these numbers. What kind of numbers should we expect? What is a typical value for the density of any common material? What is the density of water, for example? About 1000, yes. So, for example, about 1000 kgs per meter cube is water. Typical metals is higher than that, plastics, polymers, etc. lower than that, gases even lower, right? So, for air, the density is of the order of only 1 kgs per meter cube. Okay, somebody comes to you and says, I have a material with 100,000 kgs per meter cube. You need to say, slow down, something is not right. Yeah, a feel for numbers is extremely important. What about heat capacity? What is a typical number for heat capacity? Again, for water, yes, the heat capacity for water is about 4184 joules per kg Kelvin. And this is actually one of the highest heat capacities of known materials. For metals, This is for water. For metals, it's of the order of 700 to 1000 joules per kg Kelvin. In other words, metals heat up faster. You don't need a lot of heat to raise the temperature of metal compared to water. As far as thermal conductivity is concerned, typical values, I think I've said it before as well, of the order of hundreds of watt per meter Kelvin for copper, and relatively low values for plastics, polymers, etc. Okay. In the context of these numbers, we would like to measure what the thermal conductivity of a lithium ion cell is and place it in this range. Is it a good conductor of heat or is it a poor conductor of heat, and so on. Okay. Now, if I was to give you a piece of copper, it's a pure material, homogeneous material. It is expected to have the same thermal conductivity throughout, right? And it's just one material, it's just copper. But a lithium ion cell is not like that. We have already seen that a lithium ion cell comprises multiple layers of different materials, at least 5, right? Current collector, cathode, separator, anode, and current collector. So if you think of a cylindrical lithium ion cell that has a jelly roll of this sandwich of 5 materials, then the effective thermal conductivity of this heterogeneous material or heterogeneous body will be determined by the properties of the individual materials that make it up, right? If I am 30% muscles, 40% bones, and 50% blood or something like that, then my properties are determined by that proportion, right? How much of me is blood, what are the properties of the blood, and so on and so forth. Similarly, here, ultimately the thermal properties of the lithium ion cell effectively are governed by the properties of these individual materials. So let's talk about thermal conductivity first. And I also want to draw a prismatic cell in which, let's just consider a single layer cell containing 5 layers of these materials. Remember yesterday I said that this composite paper stack can be either folded into a prismatic cell or can be wound around into a cylindrical cell, right? I am interested in understanding what is the effective thermal conductivity of this stack, right? So if heat flows through this stack, what thermal conductivity will it see is the question being asked. Okay, let me define the coordinate system here. So let's say that this is the z direction and the other two are x and y. So z is out of plane, x and y are in plane. Yeah, is that okay? Yeah. We look at heat transfer from a thermal resistance point of view. So each of these layers is offering its own thermal resistance. And when we look at the flow of heat in the out of plane direction, z is the out of plane direction. Remember, this cell really looks like this. Sorry, wrong color. Sorry, wrong color again. This cell really looks like this, right? So z is the out of plane direction. In the out of plane direction, the resistances of each layer add up in series or parallel? Exactly, they add up in series. So I have resistance of the current collector, I have resistance of the cathode, resistance of the separator, resistance of the anode, and again resistance of the second current collector, 1 and 2, right? If I know the properties of each one of them, I should be able to find their resistances and add them up in series and find out the effective resistance. In other words, Ri, where I is the ith component, is given by Ti over A Ki, where T is the thickness of the ith component, K is the thermal conductivity of the ith component. Here I goes from 1 to 5. Question? Yes. Yes, we are talking about thermal resistance only. Correct, yes. Yeah, all of our discussion, unless I specify otherwise, R refers to thermal resistance, not electrical resistance. Okay. And so what is the total resistance? It is summation Ri. Correct? And this total resistance is given by total thickness divided by A times the effective thermal conductivity. So effectively the thermal conductivity is given by this expression, and therefore I can write T total over K effective, the A cancels out, is equal to summation Ti over Ki. Okay? Please feel free to ask questions at any point if something is not clear.
Every set will be behave like a single cell, and it will be connected through the connector and have the common.
Sorry, I didn't understand the question.
Like we are having the prismatic cell.
Yes.
Does it like the spiral or single boiler paper which will be folded and keep into the
Correct.
prismatic?
Yes.
Or otherwise, or it is like we are having a one cell, the connector and everything, another cell.
No. It's a continuous fold. It's a continuous fold. Do you know Maggie? If you take a packet of Maggie, the entire thing is one continuous string. Did you know that? In other words, if you are able to boil it very, very delicately, you should be able to stretch it out into one single noodle. Similarly, this prismatic cell is also one single fold. It's not multiple 5 packs arranged together. It's a single fold that goes round and round. Folding a cloth, exactly. Yes. Yes. So what happens is that each of these materials are manufactured separately. So you get one ream of current collector. These are very thin materials. You have another ream of anode, cathode, separator, etc. You bring all these reams together and press them together. Imagine take 5 papers of 5 different colors, put them together at high pressure. So you get one stack of 5 papers. You take that stack and you fold it to create a prismatic cell. Or if you take that stack and if you wind it around a mandrel in a cylindrical fashion, then you will get a cylindrical cell. Does that make sense? Cool. So here is a simple expression for the effective thermal conductivity of this cell. Keep in mind that this is the effective thermal conductivity in the Z direction. So I should call it Z. Now if the heat was to flow in the X direction, what would happen? These 5 resistances, how do they arrange themselves? They act in parallel. They act in parallel, exactly. Yes. And therefore in the, so this is all in the Z direction. In the X direction, things are slightly different. In the X direction, 1 over R total is equal to summation 1 over Ri. Instead of this expression, now this is the parallel arrangement, right? Becomes a little more complicated, but nevertheless, from here, this gives me R total is L over AK, so K effective in the X direction over T total will be equal to summation Ki over Ti. Similar expressions, but slightly different. This shows, first of all, that the thermal conductivity of the cell is expected to be different in the out of plane direction and in the in plane direction. The lithium ion cell is expected to be anisotropic in nature. Sorry, yes? Okay. Additionally, I did not talk about this too much, but I would like to introduce also the concept of interfacial thermal contact resistance. What that means is that if I have two materials, let me use two different colors, that touch each other, the contact between the two is never perfect. Even if these are very smooth materials at the microscopic level, there's always some roughness. In other words, if I was to zoom in here, the actual contact region will look like this. So that the two materials are actually in practice touching each other, not over the entire area, but over a smaller fraction of the area. Because of this imperfect surface contact, there is always a resistance to the flow of heat across this material. Imagine in the worst case, if these two materials are barely touching each other, then heat will not be able to flow across. In other words, the interface will offer a very large resistance to the flow of heat. If on the other hand, these materials are very, very smooth and they touch each other at 99.9% of the actual area, then heat will be able to flow very smoothly across the interface. What I'm saying is that at the interface of each of these materials, there will exist a contact resistance, which I will need to add here. The total resistance is not just the contributions of the individual materials, but also the contributions of each interface that occurs in this problem. We will look at that in more detail in a lecture tomorrow. But since we are talking about it here, I wanted to make an introduction to contact resistance. Okay? Let's go back to the question of measurement of thermal conductivity. So, how is K measured? If I give you a piece of copper, a thin sheet of copper or plastic or whatever, how do I measure thermal conductivity? Let's take this as an example. If I'm interested in measuring the thermal conductivity of this material, how do I measure it? Well, the thermal conductivity is governed by the fundamental equation Q equals negative K dt, Q double prime equals negative K dt dx, which in the in a one-dimensional problem could be simplified to Q equals negative K delta T over L and Ka delta T over L. In other words, if this is A, if the cross section area is A, and if the thickness is L, and if there is a temperature difference delta T across, and if that causes Q amount of heat to flow, then K is simply given by QL over A T1 minus T2. Right? So from an experimental measurement point of view, if I am interested in measuring the thermal conductivity of this body, I need to measure these 4 or 5 quantities. Which of these is the easiest to measure? No. Okay, it's easy to measure temperature, but it's much more difficult to measure temperature reliably. Okay, we have to think a little more about it. I think the easiest to measure is L and A. Right? You can measure the thickness of the body quite easily. Hopefully it is uniform, and you can measure the cross section area of the body. The challenge comes in measuring Q and the temperatures. So let's think about, as an experimentalist, how will I run this experiment? I give you this body. Where did that go? Here. Actually, this is a better example. Here is a sheet of copper or plastic. How do I run this experiment that we have in mind? It looks like this, right? So if I am just touching it, how much heat is flowing across it? Sure, yes. But let me answer this question. Let me ask this question first. Right now, how much heat is flowing through this body? 0. Why? Because the temperature is the same on both sides. Nothing is happening. So in order to force some heat to flow, I need to be able to impose a temperature gradient. If I can somehow maintain 30 degrees C on this side and 50 degrees C on this side, then some heat will begin to flow. And if I can measure how much heat is flowing, then I will be in business. Right? That's what I want to do. Or alternately, if I can force a certain amount of heat to flow across it and measure the temperature difference caused by that heat flow, then I'm good as well. You see what I'm saying? So in other words, in order to measure the thermal conductivity of this lithium ion cell, I need to hold it like this. I need to somehow make some heat flow through this and leave from the other side, and then figure out how hot does it get on the hot side compared to the cold side. Any ideas on how I can force some heat to flow across my cell? We can connect a heating plate, sure. So let's think about that. Here is my cell. What do you mean by a heating plate? So this is a metal plate perhaps. That generates heat. How does it generate heat? Sure. So it is connected to a power source, and there is some embedded heater inside it which produces heat. Okay. Then what is the next step in this experiment? What do we do next? We'll have to measure how much heat we are supplying. How will we measure that? Sure. So I can connect an ammeter and a voltmeter. Yeah, and V times I will give me how much joule heating occurs in this heater, right? Any objections to that?
We have to insulate this side also.
Sure. So the amount of heat that is generated in this heater is not necessarily the heat that passes through the cell, right? So in order to force the heat generated in this heater to go through the cell, I need to provide ample insulation. Right? What kind of insulation should we provide and how much? There are all kinds of insulation, wool, tape, etc. available out there. It turns out we learned the hard way that it is nearly impossible to provide perfect insulation. Okay? Some heat will nevertheless go away in one direction or the other. Okay? Nevertheless, there are some things that we can do to minimize it. One simple thing we can do to minimize it is to take this entire experimental setup and put this in a big vacuum chamber. Because if there is vacuum all around, then there will be no convective heat transfer and conduction heat transfer would be minimized as well. Okay? Remember that there is no such thing as a perfect vacuum. There will always be some air left behind and there will always be some heat transfer occurring because of that air. Okay? Designing an experiment and running an experiment is a very humbling experience. Okay? On paper, you think you can do everything. Measuring it with a thermocouple is easy. It's not that easy. Okay? When you actually run experiments, and I know some of you do experiments in the lab, you know exactly how difficult it is, right? Blood, sweat and tears go into running experiments. All right. What is the next step? What do we do next? So we have some idea of this term now. A and L are easy to measure. We now need to measure the two temperatures, correct? Where do we measure those temperatures and how?
And of course, you can create a number of nodes this side, number of thermocouples one side, number of similar other side. Have to take the
So where would you like me to place our thermocouples? Here?
on that surface a number of
Multiple? Okay, sure. Each thermocouple comes with two wires, right? So you're asking to have a large number of wires. Each of these wires will need to go out of the vacuum chamber, right? So you need to make sure that you have space available to pull all of these wires out, right? Each of these wires will likely break the vacuum. You'll have to seal it up effectively and all that stuff. What about on the other side? On the other side, we also need thermocouples, probably, right? Should I place these thermocouples directly on the cell or directly on the heater? Or where should I place the cells? Sorry, the thermocouples. Directly on the cell or on the heater? Or doesn't matter? Sure, I think putting it directly on the cell makes a lot of sense because the heater, you know, by the way, how will we make the heater touch the cell? Sorry? Sorry, I can't hear you too well. The example of iron. Okay. No, my question is how do I stick the heater to the cell? Here is a cell. Here is my heater. cell heater. Do I just leave it there, or do I try to push it with some pressure, put a clip on it? There will always be some resistance between the two. We are trying to minimize it, right? What are some ways to minimize that contact resistance between the two? There are these materials called thermal pastes, thermal interface materials. They're like epoxy, high thermal conductivity epoxy. You put that paste here, it sort of acts like an adhesive, and then it's like a goop. You glue it down there, right? It will not eliminate thermal contact resistance, but it will minimize it. Okay. Having done all this, what do we do next? Okay, so I have a switch here. I start passing current, and then what? Wait, you're going too fast. You know the difference between a PhD and the industry. In the industry, um, you go to your boss and say, here are these results. The boss says, you should have given me these results yesterday, right? Your PhD advisor says, you should be giving me these results tomorrow. You should be thinking more about it. Okay. In the industry, there is no time to think. They say, don't think. In academia, we say, think, don't do. Don't be in a hurry to do things. Okay. Come to think of it, all of this, once you have a plan, is very easy to do. Right? This is not rocket science. You're not trying to manufacture 5 nanometer silicon devices, right? Once you have all the equipment, the materials, once you have a plan in place, I'm sure you can put it together in a couple of days. You can get data out in other days, right? But I think the more important thing is to sit down and think about it. Okay? Think, don't do. Don't be in a hurry to do things. Because, for example, in this case, we forgot how we are going to measure the temperatures of the thermocouples. There are these maybe 10 thermocouples. How do you plan to measure the temperature of these thermocouples? So we need a proper data acquisition system to measure those temperatures. Hopefully you will use a software like LabVIEW and make a nice GUI, have nice little plots so that you are monitoring the temperatures of these cells, right? Now you go and switch this on. Suppose in your LabVIEW you have temperature plots coming out for you. What will you see as soon as you start passing current? The temperature will begin to rise, and then eventually it will reach a steady state, right? Hopefully you can see that there will be two sets of data. All these thermocouples will heat up a little bit, and they will all be quite close to each other, whereas this set of thermocouples will get much hotter. Correct? And it is this temperature difference that we are interested in. Yes? How will you determine exactly that temperature difference? How long are you going to wait to reach steady state? Huh?
That also is a challenge because ideally it will not, there will be some temperature rise.
Sure, yes, absolutely. Strictly speaking, theoretically speaking, steady state is reached at infinite time. You don't have infinite time on your hand. You have to graduate and go, right? Therefore, you have to figure out some other criteria to assume that, to be confident that you have more or less reached steady state. Typically, the criteria is to say that I do not want to see more than plus or minus some x degrees C fluctuation in temperature over y seconds. So if the temperature of a thermocouple does not change by more than 0.1 degrees Celsius over a 30-second interval, I will say that is my criteria to have reached steady state. So you can perhaps tell your LabVIEW code that look for this criteria. When this criteria is met, that is when I want to take my data. Right? Taking data is very easy, but you have to determine when and how to take your data. Right? Each of these thermocouples will also have some fluctuation and some spread within them. What are you going to do about those? Say you have 10 thermocouples on this side. What value of temperature will you obtain on this side? The average of those 10? Yeah? Is that reasonable? Sure, fair enough. Suppose one of them has a mind of their own. You know, suppose I have 9 of them nice and tight, and one of them for whatever reason is very different. What will you do about that? Replace it? Sure, yes. Replace it? Sure. It was a brand new thermocouple, so it was quite likely to work correctly, right? But anyway, let's replace it. Then what? Then if the new thermocouple also gives you this anomaly, then what would you do?
Then we will have to calibrate.
Sure, both are very good points. You have to go back and make sure that all of your thermocouples are calibrated. We didn't talk about this, but we should have been doing calibration even before we started this experiment, right? And to your point, we have to make sure that all of these thermocouples are attached correctly, there are no impurities or other problems like that, and so on and so forth. Contacts are perfect. We didn't talk about this as well. See, this is a can of worms. The more you talk about it, the more challenges you foresee in your experimental measurements, right? If you just walk into your lab and start running this measurement, good luck to you. You know, you will get a number for sure, but what kind of confidence do you have on that number? Nah. If I were your advisor, I would ask you to go back and think about it before you do it. Okay? Brings me to another question. How do I attach my thermocouple to the surface of the cell? Here is my surface. Let's go to a different sheet. Here is my cell. Here is my thermocouple. Oh, and by the way, we didn't even talk about what type of thermocouple. So if you go to, I don't know what is used here. We commonly use Omega. Omega is a well-known company. If you go to omega.com, the number of thermocouples they sell is what order? How many different products of thermocouples can you buy from omega.com? 10, 100, 1000, 10,000? Probably 1000. So you have to choose among perhaps 1000 products. You can't say ek thermocouple dena bhaiya, right? That's not how it works. It's a little too complicated. They have too many applications, too many temperature ranges, too much sensitivity, etc. And you're standing there. Imagine going to a grocery store and seeing 1000 different types of bananas, and you have to buy one banana. All you want is a banana. Just give me a banana, right? But here you have to think very carefully about what thermocouple do you use. In fact, let me take a step back. Do you even use a thermocouple? Or is there something better is there a better technique for measuring temperature that would serve you well instead of a thermocouple? Sorry? IR camera, sure. So going back to the previous sheet, an IR camera has certain advantages. What is the key advantage of the IR camera? Yes, it is not in contact. You can measure it from a distance. So you can imagine that you can have an IR camera looking at it from here and be able to measure, right? The problem is you don't have optical access on this side, right? You have a heater on top of the cell, insulation on top of it, and you cannot possibly point your IR camera to the other side, right? Let's stick to thermocouples for a little bit. One more important question in a thermocouple is, what is the size of the bead? So this bead size is also something that Omega will ask you. Do you want a 1 millimeter bead or do you want a 200 micron bead? The price is significantly different. The thinner your bead, the better your measurements are going to be, because the thermal mass of this bead plays an important role. You see, this thermocouple does not measure temperature instantaneously, right? The thermocouple that is in touch with my cell, once the cell gets hot, the bead of the thermocouple will get hot, and therefore a potential difference will be formed. This process does not occur instantaneously, and therefore the thinner the bead, the better it is. Oftentimes people will take the pain of creating a little hole, like a little dent. Sorry, wrong color. In your body, so that you can place your thermocouple very nicely into this hole. You will probably put a lot of thermal paste around it and so on. Is that possible here in our measurement? No, I can't drill a hole in my cell, right? So that's out of the question. But nevertheless, I will want to put a good deal of thermal paste all around my thermocouple in order to make a good intimate thermal contact with the surface of interest. Okay? Now, having done all this, I take a measurement, I stick the numbers here, and I get a value, say K equals 0.65 watt per meter Kelvin. Actually, this is the funniest thing that happens with my students. I'll give you a simple example. Let's say K equals Q over delta T. Let me just simplify things for a little bit. I'm trying to make a point here. Suppose you measure Q and Q turns out to be 1 watt, or just say 1, okay? And suppose delta T turns out to be 3. This is from my measurement, okay? What is the value of K? Point what? Where do you want me to stop? Where do I stop? 2 or 3? 3. Why? That's rather arbitrary, right? Suppose for example, suppose the measurement accuracy of this thermocouple was plus or minus 1 degrees C. What that means is that the 3 degrees C temperature that you measured could very well have been 2 or could very well have been 4, anywhere between that rather broad range. If it was actually 2, then your thermal conductivity would have ended up being 0.5, correct? If on the other hand your delta T was 4, then your thermal conductivity would end up being 0.25. Now here is the point. Based on your measurement, the only confidence that you have is that my thermal conductivity is somewhere between 0.25 and 0.50 watt per meter Kelvin, whereas you are proposing that I report a thermal conductivity of 0.333. That is a little too exact, given how much uncertainty I have in my measurement anyway, right? So how you report your measured value should be consistent with how much confidence you have in the certainty of your measurement. If you go back, purchase more expensive thermocouples which are accurate up to 0.1 degrees Celsius, then your thermal conductivity will be between 1 over 2.9 and 1 over 3.1. Correct? I don't know what these numbers turn out to be, but this is much tighter now, right? And you should be confident of reporting thermal conductivity to the second or the third decimal. In fact, there is a whole field called uncertainty analysis, which I will not go into in this short course. But the idea there is exactly what we are talking about here. That if I carry out a measurement, suppose z equals x over y, and suppose there is a certain uncertainty associated with the measurement of x and a certain uncertainty associated with the measurement of y, then what is the resulting uncertainty in the measurement of z? No measurement is exact, right? In addition to measuring my thermal conductivity, I also need to understand what is the spread on it. It's not just 0.33, but it is 0.33 plus or minus something watt per meter Kelvin. Reporting the uncertainty along with the actual measurement shows that I am grounded, that I understand that my measurements are not perfect, right? According to the Hindu philosophy, there are 4 types of people in this world. Those who know that they know, okay? Those are the perfect ones. The second category is those who know that they do not know. If you are not in the first category, then at least you should be in the second category. That you should know that you do not know this exactly, right? And by the way, the fourth category is people who do not know that they do not know. They are the ones usually who shout the most and speak the loudest and attract a lot of attention, okay? Don't be that type. Either be number one, you know that you know, the perfect people, right? Or you should know that you do not know. So figuring out the uncertainty in your measurement is almost as important as carrying out the measurement itself. And so you've got to have a plan for that as well, right? The other thing is repeatability is also important. Meaning that you carry out this measurement, you get a value, and you go home or go away to your hostels, come back the next day, repeat the same, exact same measurement again. Do this 3 times and see where your numbers are. If you get a value of 0.5 today and 0.7 tomorrow and 0.3 the next day, something is not right, right? Things should not fluctuate as much. What else can I do in terms of repeatability that will give me confidence in my measurements? So what I proposed just now was to go back, come back the next day and measure the thermal conductivity again. What else could you do to give me some more confidence that I'm doing things right? Sure, absolutely. So this heater that is passing current and producing heat is the thing that is driving the flow of heat. What if I double my current, start producing more heat? If I do that, then I expect that my temperature difference, if the heat flux goes up by 2 times, how should the temperature difference change? See, from this equation, K should be a constant, right? So if Q goes up by 2 times, T1 minus T2 should also go up by twice, right? So you should verify that. That's an excellent suggestion, right? At some point in time, if you start passing too much current through it, then the temperature rise will be so high that the thermal conductivity, which in principle is a function of temperature, will begin to show its temperature dependence, right? We are trying to run this measurement at room temperature. Strictly speaking, the temperature difference should be extremely small so that I am measuring the thermal conductivity exactly at room temperature. Right? In other words, I need to provide just a small puff of heat and measure the small temperature difference that occurs as a result of that. I'll never be able to do that, right? I need some substantial amount of heat to get a good measurement. But that amount of heating should not be so large that this temperature difference becomes so high that the thermal conductivity of the cell, its temperature dependence begins to appear in my measurements. But nevertheless, increasing or decreasing it by a little bit and measuring the resulting temperature difference will give me confidence in my measurement. Right? In your PhD defense, if you show one set of data and then say, you know what, I measured it slightly differently as well, and the numbers are very similar to each other, that gives your committee a world of confidence that you didn't just wake up one morning and do a measurement. You actually did it systematically and so in a systematic manner. Right? One more thing that I would do here, in addition to repeating this experiment, is to prepare 5 specimens of the exact same cell and measure thermal conductivities of 5 identical cells. Okay? And these cells need to be purchased in the same batch. Right? You don't want to do this repeatability measurement on one cell that I purchased today and another cell that was lying in the lab for 1 year, was probably leaking a little bit. Right? That's not what you want to do. 5 identical samples should give you relatively similar thermal conductivities. Does that make sense? Any questions? Yes, it is possible to do that. So the simplest way to do that from an experimental point of view, did you mean experimentally or experimentally? Yes. So from an experimental point of view, suppose I have 2 materials, a red material and a green material that touch each other. The question being asked is there some way for me to measure the contact resistance between these 2 bodies? The simplest way to do it is to basically run the same measurement on that sandwich. So I will take a heater on this side and I will embed a number of thermocouples along the length of, along the thicknesses of both materials. In other words, I will drill a hole and place a thermocouple here, 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 and one as close as I can to the mating surface. And I'll do the same thing on the other side as well. Okay? And I'll do the same thing, you know, insulation, vacuum, blah, 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 the whole shebang. In a setup like this, in steady state, if I was to plot the temperatures reported by these thermocouples, T versus Z, let's say, and let me use red color for the thermocouples on this side and green for the others, what should I expect to see? This thermocouple will be the hottest, right? And then this, and then this, and then this, and then this, right? What about the green thermocouples? The slope will change. The first thing is that the slope will change. What is the meaning of the slope? What does the slope represent? Thermal conductivity, right? So if these 2 materials have different thermal conductivities, then the slopes of these measured data will be different. So you might see something like this. More importantly, for our purposes, if this is where the intersection is, and if I was to extrapolate this data and that data as well, we will find that there is a small temperature difference at the interface. You see, if these two materials had perfect contact between them, there would be no temperature difference at the interface. That delta T would be 0. That delta T represents contact resistance. And you can determine contact resistance simply as this delta T divided by Q, the amount of heat that flows across. Did I answer your question? Compared to? Yes, yes, absolutely. There will be more uncertainty here. That said, you know, most experiments, even on measuring thermal conductivity, are not done on a single material. Even if I am only interested in measuring the thermal conductivity of the cell, I will probably want to have an arrangement like this, where this is my cell and this is some other standard material, perhaps quartz. Why? Because the thermal conductivity of the quartz is well known. If I measure the slope of, of the temperature profile in the quartz, what will that give me? Q quartz is equal to K quartz times delta T quartz divided by L quartz. Which means that by placing a standard material next to the cell, I am able to measure the heat that flows through the quartz, right? But it is reasonable to assume that the heat flowing through the quartz is equal to the heat flowing through the cell, right? So by placing a standard material, I am able to indirectly measure amount of heat that flows through the cell. And a bonus of this measurement is the contact resistance. This measurement also tells me the contact resistance. Why is it important, or why is it useful for me to have this standard material? Because remember that we said that the amount of heat that flows through the cell is given by I square R, right? But that is a very crude approximation, because the amount of heat that is generated in the heater, not all of it goes through the cell. Some of it might go through the insulation, some of it might leak here and there, and therefore I really wish to determine exactly the amount of heat that flows through the cell, not the amount of heat that is generated in the heater, because the two may be different from each other. And this is one way of measuring directly the amount of heat that flows through the cell. By doing this, I no longer have to depend on current and voltage measurements to know the amount of heat that flows through. Yes?
We are making a perfect context, and how we will place our thermocouple at the interface of each material.
That's a good point. We are not placing thermocouples at the exact interface between the two materials. We are trying to get pretty darn close, right? But at the end of the day, we are going to extrapolate this curve and meet the two curves at the intersection. Even if I had, say, just a few thermocouples, sorry for the inconsistent color, even if I had just a few thermocouples, I would still have, you know, if this is my interface, I can always make straight lines and get my delta T. Right? One more benefit of doing all this extra hard work is that I will get this data. Let me right? This data will never be perfectly linear, right? So imagine two scenarios. One scenario is where I get data like this. The other scenario is where my data looks like this, right? What does this tell me? A and B. This is experiment A. and this is experiment B. What does this tell me? A versus B. Which measurement would I trust more? Why A? Yes, absolutely. You see, from heat transfer theory, we expected all of this to be valid only in the case of 1D heat transfer. And when I have one-dimensional heat transfer, the temperature distribution is a straight line, theoretically speaking, right? If my measurement also gives me a straight line with very good variance, right, then that gives me confidence in my measurements. If on the other hand I find that my data looks like this, then what this is telling me is that heat is entering the body, but it is leaking away somewhere along the way. It's not all going in a straight line. If it was to go strictly in a straight line, then the temperature drop will be linear and you will get a tight fit here. But here it tells me that something is not right with either my measurement setup, my thermocouples, or something. I have to go back to the drawing board and figure it out. Does that make sense? Yes, question?
Previous slide, when we are talking about the battery, so we can measure the
This one?
where you consider it as a prismatic battery, and here we are measuring the thermal conductivity in X direction. We have to measure in Y direction just by seeing any one of the interface or any one of the connection we can measure.
No. In order to see, in this case, the way I have designed my experiment, the heat will flow only in this direction. Correct? It is being produced here uniformly. So the only way for it to go, and there is insulation on the top and bottom, the only way for it to go is in this direction. If I want to measure thermal conductivity in the other direction, I have to flip it over and apply heat on the Y face and force it to go along the Y direction. Right? So if I am interested in measuring the three components of thermal conductivity, X, Y, Z, I wrote that somewhere, right? X, Y, Z, then that requires three separate measurements. Okay? Oh, and measuring R, theta, measuring thermal conductivity for a cylindrical cell is even more fun, and it's even more, it throws up a lot more questions. Okay? The last thing that I want to comment here is that there are a couple more things that I can do to tighten my measurements, to ensure that I'm doing everything right. One is that, look, this heat that is produced in the heater passes through the cell, passes through the quartz, and then is removed by the air, right? If instead of it being removed simply by the air, I have like a cold plate, which is cooled by water, then by measuring the flow rate of the water and the inlet and outlet temperatures, m dot Cp delta T of the water tells me how much heat is being picked up by the water, right? So on one hand I have heat generated by the heater, on the other hand I have heat removed by the water. Did I say water? Heater. Heat generated by the heater, this is heat removed by the water, and finally from here I also have the heat passing through the quartz. I am measuring the same quantity three different ways in order to gain confidence in my measurements, right? And this three-way check can be very helpful. Suppose, I'll give you a simple example. Suppose we find this is heater, quartz, and water. Suppose through our measurements we find that 10 watts of heat enters, right? I'm just giving some numbers here. This is 9.8 and this is 9.7. Do these numbers look reasonable? Any burning problems from these numbers? Let me give you one more data set for comparison. Suppose this is 10 watts, this is 10.1 watts, and this is 10.2 watts. Is there some problem with the second set of data? Yeah, yeah. You see, in this measurement, I have 10 watts of heat coming in. How can 10.1 watts of heat pass through the quartz unless there is some other heat source, which there is not, right? I'm not heating up this cell any other, this system any other way. Maybe if I'm running these measurements outside on a hot day, that can perhaps explain this data. In which case, you should go inside and run this experiment in a away from the sun. But in a regular experiment, you cannot. It is unlikely that you'll have more heat passing through the quartz than was generated in the heater, or more heat picked up by the water than was generated in the heater. Right? This gives you yet another layer of confidence around your measurements. You see, whenever you measure something and present it to people, you have to convince them that your data is right. It's very easy to take a measurement. If you're in a hurry, I can run this measurement within a day, right? But I would much rather that you think about it for a week and then take the measurement. Take another week, take your time, but provide enough evidence to be able to prove your case. It's almost like going to the court and trying to prove somebody is guilty of murder. Look, I have this evidence, I have this CCTV footage, I have these people saying that they saw him, and so on, right? Similarly, I have 3 different pieces of evidence confirming and giving me confidence in my measurement. Then if I say that I have measured the thermal conductivity of the cell to be 0.5 watt per meter Kelvin plus or minus 0.2 watt per meter Kelvin, people will say, yes, I think you're right. We have reasonable confidence in your measurements. Okay? Any questions or comments? Yes, we have measured contact resistance, and we will talk about it probably tomorrow. We have a lecture on interfacial contact resistance, interfacial thermal transport. So we will do that tomorrow morning. Okay, very interesting topic, and we'll be glad to look into it in a lot of detail. Any other questions here? So I think this is a good discussion, and what I would like to propose is that the next lecture, which was nominally on thermal modeling, I want to modify that a little bit, and I would like to spend part of it to continue our discussion of experimental measurements, if that is all right with everyone. Yes, because my main intention actually was to discuss measurement of thermal properties of a cylindrical cell. And I'm almost out of time. This is also as interesting as measuring thermal properties of a prismatic cell. It's a little more challenging, in fact, right? In the case of a prismatic cell, I had 2 faces of the cell at which I could place thermocouples and measure temperatures and determine thermal conductivity. What do I do here? If I am interested in measuring the radial thermal conductivity, according to Fourier's law, QR equals negative KR del T del R, right? So, if I want to run a measurement on a cylinder similar to the prismatic cell, then I would have to place my thermocouples at 2 radial locations, and I would have to force the heat to flow in the radial direction, and that will give me the value of Kr. Now tell me, where do I place my thermocouples here? Here is my cylinder. Let me show you the top view. This is the center of the cylinder. What is the easiest location for me to stick a thermocouple? On the outer surface. Absolutely. So here I place one thermocouple. Where do I place the second thermocouple? No, there is no point of placing a thermocouple on the opposite direction. That doesn't help me because these two thermocouples are both at R equals R. Right? In order to measure the radial thermal conductivity, I want the heat to flow in the radial direction, inwards or outwards. And I want to measure the temperature at two R locations. Both of these represent the same R location, R equals capital R. Right? Where do I go and place my second thermocouple? Sorry? In the center? Sure. I can drill a hole in the cell and place a thermocouple in the center. The problem with that is that if I drill a hole in the cell, the volatile electrolyte in the cell will evaporate and it's not really a cell anymore. Right? This lithium ion cell is a hermetically sealed system. I cannot possibly drill holes in it. If this was a copper cylinder, sure, absolutely, that is exactly what they would do. You would drill a thin hole, put a thermocouple in the center. In fact, you'll place multiple thermocouples here, here, here and there. But that I cannot do with a lithium ion cell. The only radial location that I have available, unfortunately, is the outer surface. This was indeed the challenge that Stephen Drake and I were looking at in 2013 or so. So this other professor I keep talking about walks in, says, here is my cell, can you tell me how hot it will get? I said, okay, do you know its thermal conductivity? He said, what is thermal conductivity? I said, okay. I look at the literature, there were no reports of thermal conductivity of a cylindrical lithium ion cell. So we said, we've got to measure it. And then we were staring at it and wondering, what do I do? Our first thought was also to put a thermocouple in the center, but David Vetz, this other professor, shot it down saying, no, you can't drill a hole in the cell. That's not allowed, right? So we had to come up with a new technique for measuring the radial thermal conductivity of a cylinder where we had access only to one point. Okay? We will talk about that in more detail in the next lecture. By the way, just a few finishing points before we take a break. In that measurement, we were also interested in measuring the axial thermal conductivity of the cell. Because ultimately the interest is in determining if the two thermal conductivities are very different from each other or not. I hope you can see that measuring the axial thermal conductivity of this cell is not that difficult, right? It will in fact be very similar to this prismatic measurement that we've been talking about. So I can take the cylindrical cell, I can place a heater on one side, I can insulate the heck out of it, and I can measure the temperatures at the two axial ends of the cell, right? Along the axial direction, I do have easy access to place thermocouples at the two ends. So measuring the axial thermal conductivity is relatively easier. Measuring the radial thermal conductivity is a lot more challenging. And measuring the circumferential thermal conductivity, kill me, I can't do it. Okay? Measuring the axial thermal conductivity of a body is super challenging. My students and I have tried it and we have given up on it for now. It's one of my things to do before I retire, I hope. Okay? Yes. No, not at all.
But let's say if I do here
Yes.
and I want to measure the heat,
Yes.
so I somehow select a 2D problem. I don't know which 2D problem.
Yes.
I design some kind of 2D problem.
Yes.
For with the solution, I know.
Yes, exactly.
Here and
Exactly. Yes.
then I notice the temperature of the boundary.
And
rather than try to make it 1D problem, I actually solve a 2D problem.
correct.
I go here and I try to.
Sure, yes. That is roughly the approach we took as well. the problem we ran in was not on the theory side. On the theory side, I can formulate a 2D problem and I can solve it, and I can figure out what to expect. But the problem we ran into was in order to replicate those conditions in a real life experiment. For example, in this case, in order to force two-dimensional flow of heat in the r and theta direction, I need to place a heater only along a certain circumference, right? I don't want to put it all around. And then where do I measure the temperature? Do I measure the temperature here? Sure, perhaps, right? There were too many experimental difficulties in making this happen the way the theory says it will happen. That's the short story, you know. How do I take a heater and I stick it only to a small section and not allow, you see, I have to insulate the rest of it, right? Part of it has to be heated, part of it has to be insulated, but inevitably some of this heat will leak in this manner, and all kinds of other logistical difficulties. We said, okay, you know, to solve this problem, we said, take my cylinder and put a screen and have a radiation lamp here, so that the heat, the radiative heat passes through this slit and only influences this part of it. But there the problem we ran into was we did not know how many watts of heat is reaching the surface of the cell. In the previous measurement, I square R through the heater tells us how much heat is generated. Here we had no idea. In fact, Swapnil, who was Dr. Tyagi's MTech student, was the one who ran these measurements, and you know, I gave him a very long rope, but it was an extremely difficult measurement, and ultimately we just had to move on and do something else. The other problem here, by the way, is that most materials do not have distinct values of Kr and K theta. Ideally, to run this measurement, you need very different values of Kr and K theta to be able to distinguish between the two. But we did not know where to go and find a material with strongly anisotropic values, which you know the values of. We know that a cell, a lithium ion cell, probably is anisotropic in that way, but we don't know its values. To validate it, exactly. But then this is a chicken and egg problem. How will I ever validate it? Somebody else has already measured it, right, to be able to, for me to validate it. But then if somebody else has already measured it, then why am I doing it? Right? So all kinds of problems and challenges. We are past our time, so I'll stop here and we'll start exactly here where I'll talk about some measurements using cylindrical lithium ion cells. Alright, so let's take a good 30-minute break. We'll restart at 11:30. Small change in plan. Instead of starting right away on thermal modeling, let me discuss the question of measurement of thermal properties of a cylindrical lithium ion cell first. I think it's a good, interesting topic. It's experiments oriented, and so that is also helpful. And so we'll spend the time that it takes for us to discuss radial measurements, cylindrical cell measurements, and in the time remaining we'll go back and we'll talk about a few issues related to thermal modeling. Okay. So just a background, in the previous lecture we had talked about measurement of thermal properties of a prismatic lithium ion cell, and towards the end I had shown the difficulties. I discussed the difficulties in measurement of thermal conductivity, radial thermal conductivity of a cylindrical lithium ion cell. So let's talk about how we can measure the thermal conductivity of a cylindrical lithium ion cell, where I can only place a thermocouple on one radial location. I cannot drill a hole and put a thermocouple inside. Okay, all right. So I'm going to close this and I'm going to start a new sheet. And that would be lecture number 8. Is that right? Thermal measurements continued. So here is a cylindrical lithium ion cell. I'm showing a cross section. Actually, it's much better without the ceiling fans. Yeah? Much easier to hear and all that. I place a thermocouple here. Okay? I cannot place a thermocouple in the center, so let's skip that for now and see where we go. Right? In addition to that, I wrap a heater all around the cell. And then on top of all this, I place insulation, heavy insulation. And then I take this entire setup and put it in a vacuum chamber. Okay? Remember that according to Fourier's law, QR is negative KR del T del R. And we used a relationship like this to find out the thermal conductivity of the prismatic cell. But there I needed to have 2 measurements of temperature. Here I will only get 1 measurement of temperature, and therefore this by itself will not take me too far. Right? I've got to think of something else with which to somehow extract the thermal conductivity of the cell from this measurement. Right? For that, I think it is easiest for me to go to the paper that we wrote and follow along. Okay, so this was the first paper we wrote in the area of lithium-ion batteries. Continues to be the most cited and one of my favorites. And so let's see what we had done. So yep, this is sort of, by the way, how this is how a lithium-ion cell looks like. If you cut the cap open, this is a very tight toilet paper roll of the 5 sheets that we were talking about: anode, cathode, separator, current collector, etc. Those are very tightly wound and placed inside in a bath of electrolyte. The electrolyte is gone now, of course. These things jutting out are the current collectors that were supposed to touch the cap of the cell to make a connection. All that is gone, and this is how it looks like. The first time we saw the structure of the cell, the first thought that came to our minds was, okay, if I am a piece of heat here and if I am trying to travel outwards, then I'm going to have to jump from one material to the other multiple times. How many times? Hundreds of times, right? Going from here to here, there is one material, then the next material, so I have to jump to the next one, and then I have to jump to the next one, and so on. Every time I jump, there is a resistance, right? It's like the contact resistance. It is indeed the contact resistance, right? So that provided us some thought, a hypothesis, if I may say, that the thermal conductivity in the radial direction might be very different from the thermal conductivity in the axial direction. If you were traveling in the axial direction, you can just travel along these sheets, right, without having to jump from one sheet to the other. Whereas in the radial direction, you don't have a choice. You have to make these jumps again and again and again. So that was our motivation for measuring not only the radial, but also the axial thermal conductivity of the cell. Okay. So, like I was discussing, we took a cylindrical lithium ion cell. Oh, come on. We took a cylindrical lithium ion cell, placed a thermocouple bead at the outer surface, and then placed a heater around it. This is a thin heater, Kapton heater, also from Omega, if I remember correctly. And that is the hand of Stephen Drake, probably. Yeah. And then we put insulation tape around it, and on the two edges, the two faces, and so on. And then we placed it inside a small vacuum chamber. So this is a makeshift vacuum chamber. We basically drilled a hole to carry all the wires in and out, and then from here you can't see it completely, but from here we pulled air out to create vacuum. I don't remember the number. I think it was minus 80 kilopascals or something like that. This is plastic. This equipment is actually called a desiccator. We didn't have a proper vacuum chamber in our lab. Yeah. So a desiccator is basically a piece of equipment. Yeah. So in material science, where is the enter button? In material science, there you go. It's essentially a vacuum chamber, roughly. It is used for drying materials. So if I have a wet material, I want to pull out all the moisture. I'll put the material in here. I'll connect this to a vacuum line, and I'll pull all the air out so that the moisture has no choice but to evaporate. I had used this for something else many years ago, and we said, okay, a desiccator is as good a thing as any other in order to run these measurements. Yeah, and these are not very expensive. I mean, $2,000. And of course, we had to figure out how to seal this and all that stuff, right? A fairly crude measurement. This is not a measurement that will win me the Nobel Prize, but it gives me the thermal conductivity of a lithium ion cell, which is all I want. I don't want the Nobel Prize. Okay? So going back here is my setup, right? I have a thermocouple measurement. Actually, I can close this other one. No, let me keep that. Let me show it here. So my thermocouple will give me a temperature measurement as a function of time, right? So if I was to plot T versus time of the thermocouple, I only have one thermocouple. Initially, that thermocouple is at 20 degrees C. And for your benefit, let me just draw the setup once more. Here is my cell, here is my thermocouple, there is a heater all around it, and there is insulation on the outside. What kind of T versus time should you expect to see? Can somebody help me with that? It will increase, and then okay, so what is being proposed is that it increases and then reaches steady state. Does everybody, sorry? Steady state, yes. Does everybody agree with this, or does anybody have any other thoughts? And
we are still then temperature should rise when it.
That's a good thought. A steady state is reached when there is a balance between heat coming in and heat leaving. In this case, if the insulation is perfect and if I'm continuously supplying heat, then where is the heat supplied going? It's not going anywhere. It's being absorbed by the material continuously. And therefore it turns out that the temperature as a function of time for this problem should in fact look like this. So Stephen carried out these measurements. At this point, in all honesty, we had no idea how we will measure thermal conductivity. Okay, we cannot put two thermocouples. I said, okay, let's just put one and take some measurements. So we started taking measurements without knowing how we will use that data to determine the thermal conductivity. Okay, and the first set of data that he shows me looks pretty much like this. What do we do with this data in order to find out the thermal conductivity of the cell was the question, right? Sure, it keeps increasing forever, and at some point he has to stop the experiment too, right? Before it gets too hot, he switches off the power so that it does not get extremely hot within about 20-30 degrees C, if I remember correctly. So how do I take this data and use this data to determine my thermal properties was the question. For that, we went back to the theoretical analysis of this problem. So I can write a mathematical, I can write this problem mathematically and try to solve it in order to predict what the temperature distribution should look like. This is what I measure, right? What should it look like is the question. So if I was to go back here, in this problem, if this is the radial direction, then given that it's a one-dimensional problem, the governing energy equation for this problem is given by 1 over r del by del r of r del t del r. There is also a k here, kr, equals rho Cp dt over dt. Remember when I was teaching fundamentals of heat transfer, I had given the governing equation for the radial problem. Because there is no theta variation, because there is no z variation, therefore this is the only term that survives, and therefore we get this. This is subject to two boundary conditions and one initial condition. What are the boundary conditions? The first boundary condition is that negative k dt dr must be equal to q double prime, or rather plus kr dt dr, where q double prime is the amount of heating that is produced in my heater. Okay, if I measure the current and the voltage, I have some idea of what q double prime should be, provided all of it is going inside the body. Okay, and the other boundary condition, this is at r equals r, and at r equals 0, del t del r must be 0. We also need an initial condition, so t must be equal to t initial at the initial time. Say I start running this experiment initially at 20 degrees Celsius. How do I solve this problem mathematically was the question. And so he and I sat down, banged our head here and there and read that book and this book, and ultimately we were able to figure out a solution for this problem. Okay, I will not go into the details of the mathematical derivation here. Let me just show you the final solution. The pen? No, not really. It's okay. Let me just scroll down like this. So these are the equations that I just wrote, and it turns out that a solution for that problem is given by this. It's okay, it's all right. So a solution for the temperature rise as a function of r and time is given by three components: theta m, s and w. Theta m is this, s of r is this, and w of r comma time is this. Three components. Let's look at all three of them one by one. The third component has an exponential of negative something times t. What that means is that as time passes, this quantity should become what? Should become what? What is e? Sorry? It decaying. It should become 0, right? E to the power negative of a large number is 0. So at large enough time, this third quantity I expect to become 0. Okay, so at large enough time, this equation is predicting that the temperature at any location will become, this is a constant number, right? I can put small r equals capital R, and this becomes a constant number, and this is another constant number times t. So what my theory is predicting is that as the time goes to infinity, my theta at the outer surface is expected to become equal to A plus B t. A straight line, right? So as soon as we saw this and we saw the experimental data, it brought us some satisfaction that the theoretical prediction of it becoming a straight line is being seen in our measurements as well. So that was the first validation that, yeah, I think we are along the right track. Moreover, let us examine these expressions A and B. What is A? A is the constant quantity. It is Q double prime over KR, and this will give me R square by 4 if I put small r equals capital R. So that will be R over 4 in the denominator. This is A. And B is 2Q double prime by rho Cp R. Correct? Can you look at A and B and tell me what should we do? How does A and B help us measure the properties of this cell? Yeah. You see, suppose I do a measurement, I wait long enough and it becomes a straight line. I can find out the slope of this line, B, and I can find out the intercept of this line, A, right? If I know the slope and the intercept, the slope has Cp in it. Everything else is known. And the intercept has Kr in it. Everything else is known. So this tells me that I can measure the radial thermal conductivity and the heat capacity, both using the intercept and the slope of this curve respectively. Does that make sense? It's like killing two birds with the same stone. Single measurement with a single thermocouple, keep in mind.
It's not like idea is so simple, but just by applying it, we can measure.
Yeah, I mean the idea is not very difficult, and honestly, the way this happened, we did not know all of this from the start. We didn't start this work knowing that this is how it will go. We said we have to put two thermocouples. Oops, we cannot put two thermocouples. So what do? If you don't know how to swim and somebody throws you in the water, what will you do? You will start splashing around, right? And hopefully you will survive. That's exactly what we did. We said cannot put two thermocouples, can only put one thermocouple. So let's put one thermocouple and see what happens, right? Then we took the measurements and it turns out to be like this, and we said, okay, can we explain this based on a theoretical model? So we went on the theory side, and it took us a little bit to derive this expression for the temperature distribution. This is not a straightforward expression to derive, at least not for us. But once we did that, and once we saw that this term goes to 0, the rest of it is a straight line, that's when we were like, yes, this agrees with what we are getting from experimental measurements. And then the last line to connect was the fact that the slope and the intercept has information about the two thermal properties of the body. Yeah, that was our eureka moment. That yes, this method will allow us to measure two properties, not just one, at the same time. So I'll show you the experimental data and the theoretical model in one curve. And this is how that looked. No, sorry, not this, the next one. For now, forget about the bottom pair, just focus on the top pairs, right? The red and the black. These are two different types of cells, a 26650 cell and a 18650 cell. In both cases, I am plotting in red the radial the experimental measurements, and I am then plotting the analytical model. You can see that the experimental data has a bit of a curvature to begin with, but eventually it becomes a straight line, right? And by measuring the slope and the intercept of that straight line, I am able to get the values of the thermal conductivity and heat capacity of the body. And we do it for two different cells. In both cases, we get the same trend, that there is some curvature to begin with, but then it becomes a straight line. And if I measure the slope and the intercept of that straight line, that is all I need to make progress here. Okay? Sorry? You want to go more than 700 seconds? Yes. No, we waited sufficiently long, and we simply did not get any steady state. And by that time, you see, the initial temperature was about 25 degrees Celsius. Add a temperature rise of about 25, and my cell is now at 50 degrees Celsius, right? I don't want to heat up the cell too much more. The manufacturer said, remember, keep my cell between 20 degrees C and 60 degrees C. So as a matter of safety, we had already decided before the experiment that as soon as we reach about 50 or 55 degrees C, snap, the experiment is over. We don't want it to explode on us, right? That is the reason why we could not go on any longer. Yes?
If we heat it very slow, then we will have more defined better.
Correct, yes. But our motivation here was to finish this experiment as quickly as possible, because if you wait longer, then there would be more heat losses to the surroundings. So we thought, I don't know if this is right or not, but we thought that it makes sense to finish this experiment as rapidly as we can. Yeah? And through a bunch of trial and errors, see guys, this is the final data set. It looks very nice, clean, beautiful, but I can tell you that there are 100 such plots behind it that are not presented in the final paper, where nothing was working right? It takes a lot of hard work and trial and error, and going back home feeling defeated, and then coming back again next day full of energy, and then trying something else, and maybe that is working, maybe that is working. It's like a jigsaw puzzle. When you put the jigsaw puzzle together, it looks beautiful, right? But you have to also be cognizant of all the hard work that goes behind in putting the pieces together. Maybe this should fit with this, nah, maybe that should fit here, this, that, right? A lot of hard work did go behind these plots, which we don't show in our final papers and dissertations. Right? It's not as straightforward as the way I present it. You know what I'm saying? We also had all kinds of doubts and questions and what if we do this or what if we do that before we settle down on something that we think works well. Did you have a question? Yes. So both of these boundary conditions are specifying a heat flux, right? What is your question then? Yes. Yes. Uh, yes. I don't know. I'll have to think about it a little more. Here, the problem is clearly well defined, right? This is a physically well defined problem that must have a unique solution. If the problem was not fully posed, then perhaps there may have been infinite solutions. But this equation is faithful to this physical setup. I can always put a heater around a cylinder, and then I would expect there to be a unique temperature distribution, right? I don't know why mathematically, I don't know how to prove that the solution is unique here, right? And I don't know fully about what you are talking about. If you have something to show me, I would love to see about this fact that if there are two flux boundary conditions specified, then the number of solutions is infinite. Okay, can we take it up separately, please? Okay. Yes. Correct. Yeah, so I'm plotting the temperature rise above ambient. That is why these plots start from 0. Okay. It is very common in the heat transfer community to plot delta T and not T itself. Okay, because the T is not important. You could be running this experiment in an ambient at 20, 25, you'll get the same result if you plot delta T instead. Okay, so this is how we measured the radial thermal conductivity of the body. We ran a similar experiment in the axial direction as well. So this was a schematic of our setup for the radial measurements. Heater on the outside, thermocouple here, and insulation all around. We ran a similar measurement by flipping the cell by 90 degrees. So now we put insulation around the cell, we heat from the top, and we put a thermocouple at the bottom. This problem is in principle similar to that one. We also derive a solution for this problem. That one is given on the next page, I think. And that one is also similar. It has 3 components. This component, because of the minus sign, will go away at large times. The rest of it is A plus BT. A containing Kz, the axial thermal conductivity, B containing Cp, the radial thermal conductivity. So by measuring the slope and intercept of temperature versus time, I can find out Kz and Cp. And that data was also shown in those plots. The other two curves, set of curves, are the axial measurements. And again, the axial measurements, in the axial case also, experiments and the model are in good agreement for both cells, and therefore we can get the properties of the cell in the z direction as well. Okay? The results are summarized in this little table here. Don't read too much into that, because I don't think the heat rate was the same in both cases. It may simply have been because we were providing more heating in the radial measurement than in the axial measurement. You know what I'm saying? Q double prime, in other words, was different in the two measurements. So I don't think you can compare the two apples to apples. Okay? I think if you read the paper in more detail, it may provide the actual value somewhere. Okay? So these are measurements of 18650 and 26650 cells. Remember the nomenclature. 18650 means 18 millimeter diameter, 65 millimeter height. So these two cells have both the same height, but one of them is smaller than the other. 18 millimeter and 26 millimeter, slightly, not much. They both have the same cell chemistry, and so we do expect both of them to have roughly the same properties. And so our measurements show that the heat capacity was more or less the same. The Kz's were also more or less the same, and the Kr's are also more or less the same between these two cells. The most important thing coming out of these measurements is that the axial thermal conductivity was much larger than the radial thermal conductivity. To put this in the context of typical materials, copper is 400 watt per meter Kelvin, very good conductor of heat. Typical steels have thermal conductivity of this range. So in the z direction, the heat is able to flow very nicely, in fact. But in the radial direction, it has a lot of difficulty in flowing because of this very low thermal conductivity in the radial direction.
Can it be possible that we are, because it's a steel which is hermetically sealed, can it be possible that we, whatever that we are measuring, experimentally, it is showing the thermal conductivity of that steel only?
It is showing the thermal conductivity of everything. What I am, see, this model that I built assumes the body to be homogeneous. Right? This equation, or rather the equation above it, does not account for the steel casing and the anode and the cathode and the separator and so on. It is all lumped together in one single homogeneous material. So the properties that we are measuring are the effective thermal properties of the entire battery, including the casing, the separator, the cathode, the anode, etc. If you wanted to measure the thermal conductivity only of the jelly roll, then you would have to take that jelly roll out of the cell, or take it from the manufacturer before you even insert it into the casing, and repeat this measurement on that jelly roll. So certainly the values we get have some contribution coming from the properties of the thin metal casing, no doubt.
Because we are taking the from the analytical model.
Correct.
But the final output which we are getting, this is based on the experimental data which we are capturing.
Which is being done on the entire cell. Yes. So what that means is that any properties that you get from such measurements are not the properties of the jelly roll. They are the properties of the effective cell, considering everything. You know what I'm saying?
How you are heating, for radial heating, you have used the nitrogen.
Yes.
For axial heating,
For axial heating, we purchased a circular heater and we stuck it on one of the surfaces of the cell. So if you go to omega.com and look for Kapton heaters, they have heaters of all shapes and sizes, rectangles, squares, circles of different radii. So we just picked one which matched our radius as close as we could have, and that is how these measurements were run. Okay? Any other questions or comments? And the fact that the radial thermal conductivity of the cell is so dramatically different from the axial value has a lot of very interesting consequences. Imagine if I am a piece of heat in the center of the cell, and if you are interested in removing that heat, what would you do? What is the simplest thing you would do if I give you a lithium ion cell and ask you to cool it down? Blow air over it? Yeah, blow air over it. That air, what it is doing is that it is touching the outer surface of the cell, and any heat available on that outer surface is being taken away by the air, right? So what that means is that if you're a piece of heat in the center of the cell, in order to make your way out, you have to first get to the outer surface. It's like going to the US. There are flights leaving from New Delhi, but to be able to get to the US, I need to first go from Ropar to Delhi, right? By the way, do most people call it Ropar or Rupnagar? Okay, yeah, the government can do whatever they want. Oh, I'm being recorded, sorry. But everybody will do what they say, right? And this has happened all over the place. In Delhi, Gurgaon, right? Technically it's Gurugram or something like that, but who cares?
IIT Ropar, then you can
Okay, all right, good.
official name is
IIT
IIT Ropar.
Ropar, good, all right. So in order to get to the US, I need to first go from Ropar to Delhi, right? Once I get there, there is a lot of air flowing and I'll be able to get to the US easily, right? I hope you see the analogy between the two. The difficulty here is for me to get from here to New Delhi. The thermal conductivity of the cell in the radial direction is so poor that it takes a lot of effort for the heat. Not much of the heat is able to get to the outer surface. And therefore, this poses a significant thermal management challenge for lithium ion cells. You can fly as many planes as you want from New Delhi to the US, but if people are not able to get from Ropar to Delhi, then how will they all leave? Right? Similarly, you can blow as much cold air as you want on the outer surface. If the thermal conductivity of the cell inside is so poor, then you won't be able to remove a great deal of heat. Another consequence of that is that this cold air that is going to remove heat will do a very good job of cooling the outer surface, but the inner core of the cell will continue to remain cold. Whoever got to Delhi, whoever was able to get to Delhi is able to leave very easily because there's a lot of air flowing. But the problem is a lot of people are stuck in Ropar. The analogy here is that heat transfer is very effective on the outer surface. Whatever heat there is on the outer surface gets removed very nicely. But most of the heat in fact is stuck inside the cell, and it is causing a rise in the temperature of the inside of the cell. That is a practical consequence of this poor radial thermal conductivity of the cell. To which a thermal engineer could say, okay, if the radial thermal conductivity is so poor, why not use the axial thermal conductivity to remove heat? Right? So Amritsar airport also has flights going to the US, the axial direction. Why don't we all get people to go to Amritsar and leave from there, right? The thermal conductivity from Ropar to Amritsar is much higher. Correct? Yeah, that's one problem. The Amritsar airport is closed. They are using it for something else. A typical cylindrical lithium ion cell, the top and the bottom surfaces have already been used for making electrical connections. They are the positive and the negative terminals. So even if the heat was able to get to the top and bottom, there's nowhere for it to go from there onwards. All the air is blowing over the radial surface, not at the top and bottom surface. This is the dilemma here. I have availability of good cooling on one surface, but I'm not able to get to that surface effectively. And the surface that I'm able to get to doesn't have good cooling. And I cannot possibly redesign the whole cell in order to make the two ends available to me. Yes?
There is no tap cooling. What it means that connections they are
Yes,
means the on the top and bottom of this they are making the connections.
yes, absolutely. Tap cooling, people have looked into it, but somehow it's not become very popular. I don't know why.
So when we are going through the literature, there is conventional cooling type of thing.
Yes,
They are using the cooling,
correct.
but some of them are looking for tap cooling also.
Yes.
And it shows good results also. But I don't know what is reliable or not.
Yeah, yeah. In the last 10 years or so, the literature on cooling of lithium-ion cells has literally exploded. Hundreds, if not thousands, of papers. Which technology wins in the sense of getting into a product depends on a lot more things than just technology. Right? Just because one particular technology is superior to the others doesn't mean that that will be the one seen in real products, right? But we do what we can do, and then what happens happens. Okay. Few other things that we showed in this paper are the following. We showed a comparison of the three possible scenarios of a lithium-ion cell. This is the real scenario where the radial thermal conductivity is 0.2, the axial is 32, as it should be, what we measured, right? Then we said, okay, suppose I did not have this information. Suppose I erroneously assumed that the thermal conductivity of the cell is isotropic and it is 32 watt per meter Kelvin in both directions. Then my simulation will actually show that the cell is quite cold, when in reality the cell is quite warm. It will lull me in a sense of complacency, right? It will say all is well, no problem, whereas in reality there is a problem, right? I don't want to do that. But on the other hand, if I assume the two thermal conductivities to be 0.2 watt per meter Kelvin, that is also not good, because then it is giving me a false alarm. Too much problem, right? It's saying, oh God, your cell is about to explode, whereas it really is not. It's okay, it's not too bad, right? So in one sense over design, and in some sense, in the other sense, under design. Recognizing the fact that the two thermal conductivities are very different from each other is very important for coming up with the right design of the cell. Does that make sense? Any questions? Yes. We have provided a convective boundary condition, I think, on all the other sides of the cell, and we've assumed some heat generation rate. Let me see if I can find that information. No, I'm trying to see if we provide information about the heat generation rate in this case. No, we don't really do that. Sorry, I'm guilty of not providing all the information. Most people do that. Yeah? Any other questions or comments? The other thing that I'd like you all to notice here is the fact that the 5 components of the cell, 3, 4, 5, current collector 1, current collector 2, separator, anode, which is typically made up of carbon, graphite, cathode, which is a lithium salt such as lithium cobalt oxide, and this is some kind of a polymer. Remember we said that the measurement of the thermal conductivity value we measured is effectively a contribution from all of them, right? So the effective thermal conductivity we measured was 0.2 watt per meter Kelvin. Let me write it down in big letters here. What are the thermal conductivities of each one of them? Well, current collector are aluminum or copper that have extremely high thermal conductivities, about 400 watt per meter Kelvin. What I'm trying to do here is the following. Look, there are 5 resistances in series. 1, 2, 3, 4 thermal resistances, keep in mind. When resistances add up in series, the total resistance is governed by the one that has the highest resistance. In other words, if this is 1000 units and this is 1 and this is 0.1 and this is 10 and this is 0.05, which is the most important resistance here? The largest resistance. That is the one that I want to reduce if I can, in order to reduce the overall resistance. Right? The overall resistance is 1011.15. This is the one that is contributing most to the total resistance. I am trying to run a similar analysis here to figure out which one of these is contributing to the low thermal conductivity of the cell. Why is the thermal conductivity of the cell so low? Well, let's put some numbers. Copper or aluminum is 400 watt per meter Kelvin. Anode graphite is how much? Low or high? No, graphite is a very good conductor of heat. Graphite has very high thermal conductivity. If somebody could look it up, it will help. I don't know the exact number, but my belief is it is hundreds of watt per meter Kelvin, if not that. While we were doing this work, somebody else, David Cahill at UIUC, was busy measuring the thermal conductivity of lithium cobalt oxide. How much did you find out? Because he was also onto something. This looked like an interesting problem to him as well. And he said, okay, let me measure the thermal conductivity of lithium cobalt oxide. And he reported this number to be about 3 to 4 watt per meter Kelvin. 1500, yeah, so very high, very high. So far, which is the slowest step in thermal conduction? As this heat passes through, which material will offer the largest resistance to the flow of heat so far? The lithium cobalt oxide. It's going to pass through the copper, the graphite very nicely, right? It's going to have a lot of trouble passing through the the cathode. The last one here is the separator, the polymer, and we did not find any measurements, direct measurements on this material. And so actually Vivek Vishwakarma, who was from IIT Ropar, carried out those measurements himself. Maybe tomorrow, if there is time and interest, I can talk about it very briefly, but I want to talk about the other work that he had done in more detail. Anyway, long story short, this number was found to be 0.5 watt per meter Kelvin. So the slowest step in thermal conduction was through the polymer. However, what was surprising is that the thermal conductivity of the overall material was even worse than the thermal conductivity of the worst material. Yeah, that was surprising. Take 5 materials, put them in series, and somehow the effective thermal conductivity of the entire thing is even worse than the worst material in that series. It's like taking 5 students, putting them on a team project, and the performance of that team being even worse than the worst student on that team. Does that happen very commonly? Why? Because these 5 students don't know how to talk to each other, don't know how to work together in a team. They're working in all different directions. So their output is even worse than if I had given that project only to the worst student. Even that student would have done a better job, right? That is what is happening here. If this entire battery pack was made up of the worst material, the polymer, it would still have conducted heat better than when I gave it all these nice, highly conducting materials. Somehow the effect of adding these highly conducting materials went in the wrong direction. So we wondered about this for a while, and we thought about why this might be happening. And in fact, it was a good friend of mine who pointed this out to me, that look, what is happening here is that in addition to the resistances of these materials, when you put these materials together, there is resistance at the interface of these materials as well. So just like the example of that team of 5 kids, when I put those 5 kids together, in addition to doing the work themselves, they now have to talk to each other. The ideas have to flow from one to the other. And if they're not talking to each other, those ideas will not flow, and the performance of the entire team will be worse than the performance of single individual students. Here, the heat is able to jump very nicely across each material. But because this effective thermal conductivity is lower than this number, that gives us a hint that the heat is having difficulty jumping from one material to the other. Yes?
One more can be that we are having a liquid electrolyte and everything is porous.
Yes.
That will also reduce, and we don't know the electrolyte conductivity, thermal conductivity is also I think low.
It is low, correct, yes. The thermal conductivity of the electrolyte is of the order of 0.4 to 0.6 watt per meter Kelvin.
And these are not complete solid materials.
These are porous materials, exactly. The electrolyte is everywhere.
And when we are generally when we go for the K, theoretically calculating the from thermal resistance.
Yes.
We don't consider the electrolyte.
Yes, absolutely. But nevertheless, this low thermal conductivity cannot be explained by the electrolyte alone, because the electrolyte also has decent thermal conductivity. If the electrolyte had a conductivity of 0.1, then I could say that yes, there's so much electrolyte, it's not passing through the electrolyte well, which is why I'm getting a low value. But even the electrolyte is larger than the effective value, right? That, with some help from a friend, gave us a hint that contact resistance at the interfaces in this problem is an important consideration for us. See, our motivation at the end of the day was to increase this number. I want this number to be as large as possible. We've already seen that. Remember, when we were doing theoretical analysis yesterday, we saw that increasing this thermal conductivity would dramatically reduce the temperature rise in the cell. So there is motivation in increasing that number. Now the question is, how do I increase that number? That number is already so low compared to all of these that quite likely increasing this number will not help, right? Certainly increasing this number will not help, because this is not the rate limiting step. This is not the largest resistance. But even this resistance does not fully explain such a low value, right? And that is when, based on the insights we learned from my friend, we figured that we need to look at the contact resistances at the interfaces. We need to measure those contact resistances, and we need to see if those contact resistances in fact are the rate limiting steps in this process. Now the problem is that there are several contacts here. There is a contact between current collector 1 and cathode. a contact between cathode and separator, a contact between separator and anode, and then a contact between anode and current collector too. So 4 contacts between these 5 materials. In principle, each of these contacts offers a contact resistance, and we have to figure out which one of these contact resistances is the largest, is the rate limiting step. Okay, that is the question that I will address in the first lecture tomorrow, where we will look at this contact problem in more detail, and we'll figure out which one of these is the rate limiting step. And once we find out which one of these is the rate limiting step, remember, what is our overall motivation? Our motivation is to increase this number, right? So once I find out what is the rate limiting step, I want to also figure out how to improve that step in order to increase the overall thermal conductivity of the cell, right? All of that was summarized in an excellent paper, again one of my favorites, led by Vivek Vishwakarma, who was an undergraduate student here before he came to my lab, and that is what will be the focus of our discussion in the first lecture tomorrow. Okay, for now, since we are past time, let's stop here and take a break for lunch. We will meet at 2 o'clock, and I will talk about a slightly different topic at that time. Okay, thank you so much. आप ready हैं? चलिए तो शुरू करते हैं. Let's get started. This is lecture number 9, and the good news is that we are more than halfway through, so I'm sure we'll get done in a few days. So the question that I'm trying to answer here is that if I have a lithium-ion cell, the one major safety challenge in lithium-ion cells is that under certain conditions, the temperature of the cell can rise so much that it causes a catastrophic fire. Okay, that is typically what has happened in a bunch of accidents on aircraft and electric vehicles and consumer devices like cell phones and so on. It sort of gets so hot that it catches fire, combusts, and the whole thing blows up, and that is highly undesirable, right? That phenomena or that process is called thermal runaway. The word runaway basically means an uncontrolled rise in temperature. If the temperature of the cell, if I was to plot as a function of time, keeps rising in an uncontrolled fashion, then that is undesirable, that must be prevented, That process, that phenomena is called thermal runaway. Why does thermal runaway occur? It occurs because of the following reason. It occurs because, remember, we were talking about, this is anode, this is cathode, and we were talking about lithium ion cells going back and forth across the anode and the cathode, across the separator between the anode and the cathode, and that process of transfer of lithium ions was what was responsible for storage, energy storage, right? If I have excess energy, the lithium ions will move in one direction and they'll store all the energy in them. And when I need that energy, the lithium ions will move in the opposite direction and I'll get a current out, right? This is the regular nominal operation. This process generates a little bit of heat but not a whole lot. However, in addition to this main reaction, and I wrote the main reaction when I was introducing lithium ion cells on day 1, in addition to the main reaction, there are also a bunch of side reactions that occur in the cell. Side reactions such as SEI decomposition. So SEI, solid electrolyte interface, has been mentioned before in our discussion. It is a thin protective layer on one of the electrodes which protects that electrode from the separator, from the electrolyte, but eventually, slowly and slowly, that SEI layer begins to decompose. Another side reaction is lithium plating. And another one is the decomposition of the electrolyte and so on. These processes are undesirable because unlike the main reaction which can go back and forth, these processes are one way. They irreversibly consume lithium, okay? And that is the reason why we learned that the capacity of the cell drops as a function of time, because some of the lithium continues to get consumed in these side reactions, causing a reduction in the amount of lithium available, okay? However, in addition to that undesirable effect, another thing that happens is that several such side reactions are exothermic in nature, meaning that as the SEI decomposes, it generates some heat which will cause an increase in the temperature of the cell, okay? Now let's take a step back and look at chemical kinetics. If I have a simple reaction, let's say methane plus oxygen producing carbon dioxide plus 2 moles of water, 2, so there should be a 2 here. This chemical reaction has several characteristics. One is its enthalpy. What is its enthalpy? Its enthalpy is the amount of energy, kilojoules, released when 1 mole of methane undergoes this reaction, right? The way I have written it, it's an endothermic reaction. It's an exothermic reaction. It produces energy, right? This reaction can also happen in the opposite direction under certain circumstances, in which case it would be an endothermic reaction, okay? So there's one part, the exothermicity or the endothermicity of the reaction. The second aspect here is the rate of this reaction. The rate of reaction basically means what is the rate at which the concentration of methane changes as a function of time. The quantity in the bracket means concentration. What is the rate at which the concentration of methane changes with time? And typically for first order reactions, this is given by negative K times the concentration of methane itself. Meaning that the more methane I have, the faster will the reaction occur, right? What is the quantity, what is the units on the right hand side? The right hand side has units of kg per meter cube per second. How many kilograms per meter cube of methane is being consumed every second? That is given by, it is proportional to the concentration of the methane itself. If I have more methane, the reaction will happen faster. Okay, and this constant, the proportionality constant, is called the reaction rate. If the reaction rate is large, more methane will be consumed every second, and therefore more energy will be produced, because remember, this has units of kilojoules per kg of methane. So if K is large, the reaction will happen very fast and a lot of energy will be produced per second, right? The final piece of the puzzle that I'm trying to put in front of you is that this reaction rate constant K is a function of temperature for most reactions. Remember, we said that most reactions occur faster at higher temperatures. That is why food spoils faster in the summer than in the winter, etc., etc. So the same reaction, if it occurs at a higher temperature, will generate a lot more heat. This relationship is actually highly non-linear. If I was to plot K as a function of temperature, it looks like this. Meaning that for a little bit of initial period, K will hardly change. But once it sort of reaches a threshold, maybe somewhere here, until here things were okay. K was almost constant. But beyond that threshold, it just takes off very rapidly, very violently. Mathematically speaking, Arrhenius was the person who described this relationship as K equals K naught exponential of negative E over RT, where EA is the activation energy of the reaction. K naught is the pre-exponential coefficient and T is the temperature. R is the real gas constant, the universal gas constant, sorry. So what this means is that as the temperature goes up, this reaction will generate more and more heat. That is true for almost all reactions, including these side reactions that I wrote for a lithium ion cell. So if this cell is at 30 degrees Celsius, then we are sort of here. These side reactions are happening, but they're happening so slowly that they hardly generate any heat, and I don't have to worry about it. But if for whatever reason the cell temperature begins to rise, then even here I am quite okay. But if I exceed this threshold, then what will happen is that these reactions begin to happen faster and they begin to generate more heat. And what is the practical consequence of more heat being generated? It is that the temperature of the cell rises. So moving slightly beyond this threshold causes a temperature rise, which causes you to come here, where the reaction rate is even higher, and therefore even more heat will be generated. And if more heat is generated, then the temperature will go up even more. It's a positive feedback problem, right? It's like if I eat more and eating more makes me eat more, right? If I feel more hungry, if I have eaten food, then I'm in a lot of trouble because I'll never stop eating. Fortunately, we all feel less hungry when we eat more, and therefore we stop. This system is the opposite. This system is liable to not stopping at all. The only saving grace for this system is that, look, in this cell, as the temperature of the cell increases and it starts generating more and more heat, if I am cooling this cell well enough on the outside by blowing air over it or something like that, then perhaps this additional heat being generated by the cell will be removed before it causes a rise in the temperature of the cell. If that can happen, then perhaps the cell will survive. Otherwise, it will get stuck in this feedback loop where more heat generation causes more temperature rise, which causes more heat generation, which causes even more temperature rise, and so on, eventually causing thermal runaway of the cell. Okay, so that is the phenomena of thermal runaway. It basically occurs because of Q being a function of temperature. If I had a lithium ion cell with constant heat generation, this would not be a problem. Because if the cell has constant heat generation, the temperature will rise, but eventually it will reach a steady state. Right? Imagine if I have a body that generates some heat. The simplest example would be a resistor. Okay, so I have a resistor with a constant resistance. I pass current through this resistor. Yeah, this resistor will generate heat. Its temperature will rise, but it will eventually become constant. If I pass more current through it, if the heat generation is larger, its temperature will rise to a greater degree, but eventually it will reach a steady state. So if Q is not a function of temperature, for a constant Q, thermal runaway is not a problem. Thermal runaway is a problem only because Q is a function of temperature. As the temperature goes up, Q does not stay constant. It goes up with the temperature, which causes further temperature rise, which causes further increase in heat generation and so on. Right? That is the main crux of thermal runaway. It's a common problem, and it's a problem in lithium ion cells that has attracted a lot of research in the past 10 or 15 years. Both from an experimental point of view, if I give you a cell, you want to understand whether this cell is subject to getting into thermal runaway or not. Is this a safe cell or not? Under what conditions will this cell be safe? And under what conditions will it not be safe? So there is a line of research in which people do experiments in which they take a cell and they abuse it in some way or the other. Imagine I take a cell and I throw it into an oven which is at a very high temperature, 150 degrees C or something like that, right? That oven will begin to heat up my cell. And eventually, remember this Arrhenius curve that I showed. If my cell is sitting here and if I externally heat it up, then I am pushing it closer and closer towards thermal runaway, and eventually the cell will explode, right? There are people who do that as part of their research. You have to have a fireproof chamber, an explosion-proof chamber, inside which you put your cell, and then you watch what happens to the cell. It literally at some point will begin to, puff up a little bit. At some point it will rupture. Hot volatile gases will start coming out of it. The thing will catch fire, and boom, the whole thing just blows up. Question? Yes. Is it always true? Is that what you're asking? Not necessarily. First of all, it depends on whether oxygen is available or not, right? So if one tiny little cell in a large battery pack deep inside undergoes thermal runaway, if there is not enough oxygen, then it might rupture, the volatile gases might come out, but there may or may not catch fire, right? So whether there is fire or not depends on conditions. It does not necessarily mean, thermal runaway does not necessarily mean fire. It might just smolder and then just fail. The cell will fail at least, at the very least. Okay? So people do all kinds of abuse experiments in which they cause some kind of abuse of the cell, either thermal abuse, or it is also common to carry out mechanical or electrical abuse. So imagine I take a cell and I take a hammer and I patak, put a hammer on the cell. This is done in order to simulate conditions in an in case of an accident of an electric vehicle, imagine an electric car comes and crashes into something, right, a pole or whatever, and it crushes the cells, and that is sort of like a hammer hitting the cells. Another experiment that people do is nail penetration. They take a nail and they drive the nail into the cell, and that causes a very dramatic failure of the cell, because the nail, which is typically metallic, as soon as it enters the cell, it'll go through all the 5 layers which you were trying to keep separate, and it will cause a short through the layers, and that causes a dramatic short circuit inside the cell, and the cell blows up. Through all of these experiments, people are trying to understand the nature of thermal runaway. Now, one problem with thermal runaway is that these experiments are very difficult to do, right? These are not experiments that you want to run casually. There is scope for fire, explosion, all kinds of bad things can happen, and therefore these experiments are not straightforward to do, and that is why there is a lot of emphasis for developing predictive tools for thermal runaway. If I cannot test every cell for thermal runaway, then can I somehow predict whether thermal runaway will happen based on theory? And that is sort of what I will cover in today's lecture. Okay? Any questions so far? All right. So, from a theoretical point of view, what I would like to do is to predict the conditions in which thermal runaway may occur. So, imagine I have a cell of radius r, and suppose I give you this Q as a function of temperature plot. Highly nonlinear plot. And suppose I tell you all the other information about the cell. Suppose I tell you that its thermal conductivity is K, and so on and so forth. Suppose I also tell you that I am cooling it on the outer surface with some velocity u, air, etc. And the question I ask you is, will this cell be safe or not safe? Will this cell undergo thermal runaway or not? You can imagine that this cell is being pulled in 2 different directions. Q is trying to push it into thermal runaway, correct? Whereas K and H are trying to pull it back. The higher the value of K, the easier will it be for the heat to get to the outside surface of the cell. The higher the value of H, the easier will be for the heat to be taken away, right? So K and H are trying to pull the cell, don't die, and Q is saying die, right? Which of these two is dominant will eventually decide whether the cell is safe or it is not safe. And it is our goal here to try and predict that. I want to be able to write a simple equation which predicts or governs the safety of the cell. Can I write something like Q must be greater than 2kH over R for safety? No, actually it should be the other way around, yeah? Q should be less than for safety. My goal is to derive a simple to use, easy to use relationship that obviously is wrong, by the way. that is the wrong relationship. But can I write some relationship like that in order to be able to make progress? That's my goal, okay? So let's analyze this problem theoretically and derive an exact solution for this problem, which will help us understand whether this problem is stable or not. Okay, so I will write for this problem the governing equation again, del by del r, 1 over r del by del r of K del T del r plus Q, which is a function of temperature, is equal to rho Cp del T over del T. This is the governing energy equation which I had introduced on the first day for a cylindrical coordinate system. I am assuming the body is infinitely long. I am assuming the body is axisymmetric, which is why I dropped those two terms on the left hand side, and this is a relatively simpler equation. Q of T, remember, is Q naught times e to the power minus EA over RT. That is an extremely non-linear term. And if you've taken a class in applied mathematics, you might remember that non-linear differential equations are much more difficult to solve compared to linear differential equations. As a result, the standard practice when you look at a non-linear equation is to say, okay, can I somehow approximately write it as a linear equation instead? If so, then that is better. If so, I will be able to hopefully solve the linear equation much easier than the non-linear equation. So for that, what we do is, this is written as Q of T, instead of rising like this, is approximately written as beta multiplied by T. So this very non-linear equation has been approximated by a straight line instead. Beta is some constant. Slope. Beta is, as you can see, beta is the slope of Q versus T. Beta represents how fast does Q rise with temperature. We know, right, that for any chemical reaction, the amount of heat that it generates is a function of temperature. If this reaction happens at a higher temperature, it will happen faster, it will generate more heat. And what beta captures is how much does Q increase with temperature, right? How fast does Q increase with increase in temperature? What are the units of beta? Watt per meter cube per Kelvin. For every 1 Kelvin rise in temperature, how many watt per meter cubes of additional heat starts getting generated is what beta captures. Realistically, I want beta to be as small as possible. If beta is 0, good for me, right? If beta is 0, then I don't have to worry about a stability problem. If beta is 0, then the problem will have a steady state temperature field. The temperature will never go up the way I described it on the first slide, right? So this is for beta greater than 0. For beta equal to 0, it will probably look like this. The question is, if I start increasing beta, at what threshold value of beta will this curve change its nature from concave to convex? Or is it the other way around? Whatever. From this side, from this way to the other way. At some point it changes its shape. And that is the point that I want to find out. That is the maximum beta that my cell can tolerate. Any value of beta greater than that threshold, my cell will explode, right? Then I can go tell this to my electric car company and I'll say, look, please only choose cells for which the value of beta is less than that, and your car will be safe. Otherwise, I don't give you any guarantees. So what we would like to do is to solve this equation and ask ourselves, what is the nature of the resulting temperature distribution? Okay? No, beta basically captures the chemical reaction right? Beta captures the chemical reaction, and therefore beta is not related to how well you're cooling the cell. Beta is only related to the chemistry happening inside the cell. So once you have fixed the chemistry of the cell, beta is fixed. Whether you cool it well or cool it not very well does not change the value of beta. Okay? Any other questions?
K you have defined reaction rate.
Correct.
That K is dependent on temperature, so you are figuring out that as temperature will rise, the K is rising, and then the heat generation.
Exactly, exactly, because the heat generation depends on how fast does the reaction happen. If I consume 1 grams per second of methane in this case, versus if I consume 1000 grams of methane per second, in the second case, more heat will be generated. Any other questions? So let's write this equation again, and let us attempt to write a solution for this equation. 1 over r del by del r of r del t del r plus beta times t, and there's a k here, equals rho Cp del t over del t. The boundary conditions are dt dr must be 0 at r equals 0, and the other boundary condition is negative k dt dr must be equal to h times t at r equals capital R. This is the convective boundary condition on the outer surface. H refers to how well you're cooling the cell. So whether you blow air at 1 meters per second or 10 meters per second changes H. Does that make sense? So, and the initial condition is T equal to 0. Sorry, T has some initial temperature at the initial time. So initially the cell is at 60 degrees C or whatever the value may be. And now I want to find out how the temperature of the cell will change as a function of time. It turns out that there is a standard way of solving equations like this. It's called the separation of variables technique. Sorry, what? Yes, exactly. Here T actually refers to the temperature rise over ambient. It turns out that that is such a standard assumption in the heat transfer community that people don't even bother to specify that it is temperature rise. In fact, in many papers they'll even refer to it as temperature, assuming that the reader is aware that this is actually temperature relative to the ambient. I will not go into the details of the separation of variables method. That most likely you've already seen somewhere, right? Has anybody seen SOV, separation of variables, in an applied mathematics class? Yes, even in transient heat transfer, yes. That is where separation of variables method can be used for solving problems. A textbook like Kreyszig, Applied Engineering Mathematics, Kreyszig, or a book like Ozisic, which is specific to heat transfer. It has all the details of the separation of variables method. Let me not go into the details because I think I want to focus on the battery problem instead. It turns out that this problem has a solution. T of r comma time is given by summation Cn, n going from 1 through infinity, J0 of lambda n r over r exponential of negative all right, let me just download the paper because I don't want to make a mistake here. Oh no, sorry, the wrong one. Krishna Shah was a PhD student in my lab. Divya was an undergraduate student, fantastic undergraduate student. Divya went on to do his PhD at Berkeley. He's now a postdoc at Stanford. Krishna did a couple of postdocs and now he's an assistant professor himself at University of Alabama. And he will soon have graduated a PhD student himself. So I'm close to becoming an academic grandfather. It's a good feeling. So in this paper, we did this analysis. And I pulled it out because I wanted to pick up the right expression. Exponential of alpha beta by kr k over rho Cp beta over kr minus mu n squared over r squared t. Yep. Where lambda n's are the eigenvalues of this problem. Eigenvalues and eigenfunctions are a very fundamental concept in applied mathematics, right? So lambda n's are eigenvalues. Actually, this is not mu n, this is lambda n. Isn't that right? Yeah, the paper calls it mu n. That's okay. And there isn't a minus sign here. Good. And the paper calls it kr. I'm calling it just k so I can remove this r from here. Alright, I think we are good to go now. Here, lambdas are eigenvalues that can be obtained from the cooling conditions. So lambdas are, these are functions of h. For any given value of h, I can find out the values of lambda. How we do that, I'll not go into in detail here. Okay, let's focus on our intent of understanding thermal runaway instead of the mathematics, right? This is the final result. What is interesting here is that this is an infinite series, right? Infinite number of terms. Each term has a exponential component. And this exponential component in turn has a positive number and a negative number. If this positive number is greater than the negative number, then on the overall, this term will look like e to the power maybe 3t. And what is exponential of 3t as t goes to infinity? Infinity, yep. If I plot e to the power x as a function of x, e to the power 0 is 1, it's an infinite, it goes to infinity. So what that means is that if this term dominates over this term, then overall this term will be positive and I will have, the temperature will become infinite at large times. On the other hand, if this term is smaller than this term, then you have exponential of negative 3t, something like that. And e to the power minus x as a function of x starts at 1 and decays to 0. Which one would I rather have? The first or the second scenario? I really want the second scenario, right? And keep in mind that this is an infinite number of terms. So I really want the second scenario for all of those terms. If it turns out of these infinite number of terms that all of them except one go to 0, but only one goes to infinity, then the total sum will go to infinity, right? In other words, in order to ensure that this total sum is not going to infinity, I must make sure that every one of these terms must be less than 0. In other words, I must have, for stability, beta over k must be less than lambda n squared over r squared for all n values. Okay? It turns out that lambdas, lambda 1, lambda 2, lambda 3, lambda 4 is an increasing series. Lambda 1 is the smallest, lambda 2 is greater than lambda 1, lambda 3 is greater than lambda 2, and so on, right? Roughly speaking, just to jog your memory, if I have a problem like, no, not this. If I have a Cartesian problem with the temperature is 0 on both sides, then my eigenvalues are sine of lambda x, where lambdas are n pi over L. Yeah, does this bring back any memories? Lambda is equal to n pi over L, where n is 1, 2, 3, 4, 5, and therefore lambda 1 is pi over L, lambda 2 is 2 pi over L, and so on. It's an increasing series. The smallest lambda is lambda 1. And so we can make a mathematical argument here that if this relationship is satisfied by lambda 1, then it will clearly be satisfied by lambda 2 as well. Right? If beta over k is smaller than lambda 1, and if lambda 2 is greater than lambda 1, then obviously beta over k will also be less than lambda 2, and so on. Right? In other words, in order to ensure that this requirement is satisfied for all n, I can require simply that beta over k must be less than lambda 1 squared over r squared. That is sufficient. I don't have to worry about lambda 2, lambda 3, lambda 4. If lambda 1 satisfies it, everybody else satisfies it too. Okay? I can simplify this by writing it as beta r square over kr, sorry, I just want to call it k. Lambda 1 squared must be less than 1 for stability. So here we have derived a straightforward mathematical criteria to predict whether the problem is stable or not stable. If this quantity on the left hand side, if I calculate it and it turns out to be less than 1, then I can stay confident that the problem will be stable. And if it turns out to be greater than 1, then this problem is unstable. What are the units of the quantity on the left hand side? What should be the units of the quantity on the left hand side? It should be dimensionless, because the quantity on the right hand side is dimensionless. Therefore, so should be the quantity on the left hand side. There is no sense in saying 2 apples equals 1, right? 2 apples cannot be equal to 1. 2 apples could be equal to 1 rupee or something like that, which it is not. 2 apples is how much? 100 rupees, maybe more, something like that, right? But any equation must clearly satisfy dimensional, it should be dimensionally consistent. If the quantity on the right hand side does not have any units, then the quantity on the left hand side should not have any units either. And we can verify that Lambda 1 has units of 1 over meter, I think. So the total quantity as a whole, remember the units of beta are watt per meter cube per Kelvin, R has units of meter square, K has units of watt per meter Kelvin, and lambda 1 has units of 1 over meter square. What went wrong here? Watt per meter cube per Kelvin, meter square, watt per meter Kelvin, meter square. I'm leaving a meter behind. Yes. Why is that happening? Let's make sure that we copied this result correctly from the paper. What are the units of beta over K? Watt per meter cube Kelvin, and this is watt per meter Kelvin. So that is 1 over meter square. I think lambda is unitless. Yeah, sorry, my bad. Yes, lambda is unitless here. Yeah. So if lambda is unitless, then as far as the units are concerned, I don't have this. No, sorry. This is there. What I don't have is this. And then it makes sense. This is unitless as one would expect. Alright, so a practical consequence of this is that we have combined the various parameters of the problem into one straightforward non-dimensional number, which I can calculate in order to predict whether the problem is stable or not. Okay? The literature in heat transfer and fluid mechanics is full of such non-dimensional numbers, right? Which is perhaps the most common non-dimensional number out there? Reynolds number. Yeah, we see the Reynolds number all the time. What is a non-dimensional number which is involved in an inequality like this to determine something? When that number is less than 1, something happens. It's the BO number, Biot number. The Biot number, which is defined as HR over K. If this is less than 1, then what does that mean? Much less than 1, in fact. Sorry? Lumped, exactly. It means that the body is thermally homogeneous or lumped. If I have a cylinder, if HR over K is much less than 1, it means that the temperature everywhere in that cylinder is the same. But if HR over K is much greater than 1 or just greater than 1, then it means that it is not lumped. Similarly, we are proposing this number, which if it is less than 1, the problem is stable. If it is greater than 1, it is not stable. Okay? And if I stare at this a little more, what are the different components of this? Remember that mu1, sorry, am I using lambda 1, right? My apologies, I'm going back and forth in the nomenclature. I was using mu1 in the paper and I'm using lambda 1 here. Remember, in the previous slide I said that lambdas are functions of h. In fact, if I was to plot lambda 1 as a function of h, if I was to plot lambda 1 as a function of h, it is a curve that sort of looks like this. It saturates. So this non-dimensional number has multiple components. This is heat generation. This is thermal conduction inside the cell. This is convection outside the cell. Whoa. Tell me if we have to run away. And R square, sorry what? R square is the geometry of the cell. Remember I had said that this cell is being pulled in two different directions. There are some parties that are trying to push it to thermal runaway. There are some parties which are trying to make it to save it. All of those parties come together here in this manner to decide who wins. If beta is large, this must be less than 1 for stability. If beta is large, this number will grow and it might exceed 1, correct? If R is large, then also this number will grow and might exceed 1, which means that a cell of this diameter is better than a cell of this diameter. If you want to prevent thermal runaway, make smaller cells. Don't make one giant cell, instead make a large number of smaller cells and connect them all in series or parallel or whatever you want. Okay? Make sure that beta is as small as possible. If beta is 0 or negative, then this will happen for sure. This condition will always be satisfied if beta is 0. And so if I have a lithium ion cell in which these side reactions do not satisfy the Arrhenius kinetics or satisfy it only weakly, WEAKLY, not WEEKLY, then nobody got the joke? Good. Then also I will be safe. Okay? Let's look at the denominator then. In the denominator I have k and I have lambda 1 squared. If I increase k, then the denominator will go up, the entire quantity will go down, and it will be in my favor. So I want to have a high thermal conductivity of the cell, as high as I possibly can. If I can go from 0.1 watt per meter Kelvin to 1.0 watt per meter Kelvin, I would have reduced the value of this non-dimensional number by 10 times, right? And that would be very much appreciated by the cell. The final quantity is lambda 1 squared. Lambda 1 also increases with h, which means that if I blow more air over it at a higher velocity, h will be larger, and as a result, lambda 1 will be larger as well. And that is again in my favor. In fact, it is lambda 1 squared, so that's even better because it's a square quantity. If I can manage to increase lambda 1 by 10 times, this non-dimensional number will reduce by 100 times, right? So you can see that a simple analysis like this allows us to focus our efforts. It's telling us what is important and what is not that important. It's telling me that reducing the radius will help a lot because it is R square, right? If instead of a 10 centimeter cell, I can do a 1 centimeter cell, then I will almost eliminate thermal runaway. Question? Okay. Any questions so far?
We can give a name to this number of
Let us decide what name to give to this number. Tell me. GIAN number? If we had come up with this during this course, yes, we could have. This was published, in 2016. And the funny story about this, I was telling this, I think, in yesterday's lecture as well. The funny story about this is that the basic idea for this analysis, not the details, but the basic idea came to me at 11:45 p.m. on 31st of December 2015. I remember it exactly because we were having a New Year party at our home, and people showed up at 7, 8, and we had a party, 8, dance, whatever, and by 11 o'clock people were tired. They were all sitting waiting for 12 o'clock to come, right? So everybody was very quiet, sort of tired. I was also sitting and my mind was racing around these ideas. My student Krishna and I at that time were, we were just about getting to learn about thermal runaway. And we were trying this and trying that, trying to get a better idea of the problem. And these thoughts were swirling around in my mind. And as soon as I sat down and had a break from all the food and the dancing, is when this bulb, flickered in my mind that yes, I think perhaps if I do this, if I do that to that equation, now it all looks very simple, right? But if you don't know anything, then it's all very complicated and you don't know where to go, right? Now things have become very clear. We've written a paper on it and it's very clear to teach, right? It's very easy to teach this now. But at that time, ideas were swirling around in my mind, and I had a vague idea that this will work. I had a vague idea that if I do this, then I will be able to derive a criteria for stability, right? So I felt very happy, but then very quickly after that, it was 12 o'clock, and we got busy with, yay, Happy New Year, blah, 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 and then went to sleep. 2 days later, I went to my office and I called Krishna, come, we need to talk. And so he and I sat down and we systematically carried out that derivation, made sure all our steps were correct, etc., etc. And we were indeed able to show that we can derive this very simple non-dimensional number. That is the story of, we called it the thermal runaway number. And I have seen at least 2 or 3 other people call it the same. Citing our work, they say, this is the thermal runaway number, and they do some additional analysis on it. So perhaps it will catch up and the community will begin to call it the thermal runaway number. Any questions? Now, all this analysis was carried out under very highly simplified conditions. What was my geometry? My geometry was a very simple cylinder. We know that that is not the case. In reality, this cylinder looks more like a spiral roll of multiple materials inside a can, right? In reality, beta is not a constant. Beta is the slope of this curve, right? This curve is actually highly nonlinear, which I approximated with just a straight line. So real life is much more complicated than this very simple model that we have developed. And so since then, some of my students and I have tried to make our calculations more and more realistic and faithful to real life conditions rather than this very simple homogenized model. Nevertheless, the homogenized model does give us good insights into the fundamental nature of the problem, right? This very simple non-dimensional number has a wealth of information in it. It tells us how various parameters of the problem affect it. It tells us that the geometry plays a very important role. R square, not just R, but R square, and so on and so forth. So the value of simplified analysis is still very much there. Even if it does not capture all the physics of what is going on, it at least points us in the right direction. Okay, any questions?
So in this cell, there is two production, energy production as well as the current production. Current or something.
Heat generation and current, yes.
So if I will check the selectivity of this reaction, because completely the beta is a function of chemistry or reaction.
Yes.
So some of the decomposition will reduce the cycle of the day. You know, there is two cycles, charging or discharging.
Yes.
So it is like to function to fragment of this beta in future. There is any possibility?
What do you mean by fragment of beta?
There is some like beta like to split. The term of this I am talking about earlier. Is there any possibility to?
Sorry, I don't understand what you mean by the splitting of beta.
Like
Can you please?
You say that the chemistry is a part of chemistry or the chemical reaction.
Yes.
So if I split the something like to favorable, which is produce the current, or like to
Yes.
or something else to energy production, which is unwanted.
Sure.
So is there any possibility to split?
So are you asking whether I can change the value of beta?
Change, make it efficient. Something correlate in this manner, make it efficient for chemists for
so that the value of beta
the
decreases.
selectivity what is like to go over.
Sure. Certainly, yes. A chemist can answer that question better, because basically what is happening here, as I showed on the first slide, is that there is the main reaction that is occurring, and there are side reactions. If I understand you correctly, what you're proposing is, can we somehow force more lithium to be used in the main reaction and less lithium to be used in the side reaction? Beta is coming from here, beta is not coming from there, right? So if I can have the main reaction dominate over the side reaction, then the value of beta may decrease. Okay, and the answer to that is yes, probably. How do we do that? That's a question you should ask a chemist, right? A chemist. I see. Okay. Possibly. I don't have that expertise, so I don't know how it works. But chemists can do wonders. They can do a lot of good things. If they can somehow coax this main reaction to happen faster and depress the side reactions, then certainly the value of beta will decrease. By how much? I don't know. That's for a chemist to answer. Okay? Any other questions or comments? All right. So one thing that we have done in our lab, and others have as well to some extent, is to account for the multilayer nature of the cell. Remember I said that the real cell looks like a jelly roll, whereas we have modeled it here like a homogeneous body. So can I somehow account for the multilayer nature of the cell? So for that, the analysis we did, and this analysis that I will show you is the product of COVID. We did this during COVID, where we could not go to the lab. We were all sitting by ourselves, and that is when I got interested in theory, and my student and I cranked it out, and it was an interesting time, to say the least. So what we want to do here is to imagine that I have a cell with n number of layers. So I have a n layered cell. Each layer, suppose the nth layer here, has its own beta n, has its own thermal conductivity Kn, has its own thermal diffusivity alpha n, and so on. and of course has its own thickness as well. Let's call this Ln. Okay, and let's say that this entire cell is being cooled on both sides with some convective heat transfer coefficient H. Then the question is this multilayer cell thermally stable or not? You can see already that this problem is a lot more complicated than the previous problem that we had discussed. That was a baby problem in some sense. Yeah. In order to solve this problem, I need to write down the governing energy equation for every layer. Right? So for the nth layer, the governing equation is d2Tn by dx2 Kn plus beta n T n is equal to rho n Cp n. Let me remove alpha from here. I have not introduced alpha, so let me not confuse you all. This is rho n and Cp n times dTn over dt. This is for n equals 1, 2, all the way to n. That's the equation I must solve for every layer. Right? What boundary conditions do I write for this equation? Well, yes. Yes. So the first layer has a boundary condition that can be written in terms of H, right? But what about an internal layer, which really doesn't have a boundary? In that case, we don't write boundary conditions. Instead, we write interface conditions. So at this interface and at this interface, certain conditions must be satisfied. For one, if I have two bodies that are touching each other, in the case of perfect thermal contact between the two, the temperatures of the two bodies at that point must be equal to each other. So at this point, I must have Tn minus 1 equals Tn, and at this point, Tn must be equal to Tn plus 1. Not only must the temperatures match, but the heat fluxes must also match. Because the amount of heat that passes from in this layer must be equal to the heat that passes in that layer, right? I cannot have mismatch of heat flux. So in addition to this, I can also write Kn minus 1 dTn minus 1 dx. Sorry, I'm running out of space here. Equals Kn dTn dx. I have better space here. Kn dTn dx must be equal to Kn plus 1 dTn plus 1 dx. This is a considerably complicated problem to solve. It is not my intent to solve this problem here. You can look at the paper. Let me pull it out real quick. Are we doing okay in terms of the internet? I didn't quite work. Last thing I'll try before I give up is this. If not, it's okay. We can just keep going. This problem is fairly complicated to solve, not my intent to solve it. I will simply state that the solution for this problem is roughly of this form. Tn of x comma y is equal to summation Cn an cosine lambda x plus bn sine lambda x times exponential of, this lambda should be called mu here, negative lambda n squared t. The paper has all the details. The derivation was quite messy. Let me see if I can find it. Yeah, I'm close. Yeah, there, this one. Mohammad Parhizi was a PhD student at that time, just about to graduate. It was, I think, his last paper. He works at Tesla now. Girish Krishnan just finished his PhD like a few months ago, and he works for a small battery startup company that does God knows what. And Long Zhu was a visiting scholar in our lab from China at that time. He's now back in China. He and I still happily write papers. He, by the way, his English is extremely poor, so it's very difficult to actually talk to him. You know, we always talk to each other via email. So I write a long, nice email to him with very simple words so that he understands. And he, I think, uses some sort of AI to translate or whatever. And sometimes his translations are very funny. But he and I share a love for stuff like this, and so we keep working together. So anyway, here is the problem that I wrote, and the solution for this problem is of this form. And you can see that the math is fairly messy, okay? But let the mess not detract you from the basic idea. The basic idea is that in this solution, lambda n's are the eigenvalues of the problem. And if you remember eigenvalue analysis from some class that you may have taken, how are the eigenvalues determined? Suppose, let me give you a very simple problem. Suppose I have a body with t equal to 0 on this side and t equal to 0 on the other side, and I solve this problem. This is L. The eigenvalues are given by the roots of sine of lambda n x over L equals 0. And therefore lambda n is n pi. Lambda n, sorry, the eigenequation is actually just lambda n equals 0, the roots of the sine function, right? Therefore lambda n is n pi. How do we come up with that? We basically plot the sine function, sine of lambda n, and we find that it crosses the x-axis. This is lambda n. It crosses the x-axis at pi, 2 pi, 3 pi, and so on. That is how we find the eigenvalues of the problem. In this case, in the problem we are considering here, the eigenequation is extremely complicated. Maybe I can point it out to you here. No, actually the eigenequation is too cumbersome for me to write here, so let me skip that. But there is an eigenequation which I can plot, and I can check where does it cross the x-axis. Everywhere it crosses the x-axis is where the roots, the eigenvalues lie. So when we did that, Let me see if I have that plot here. When we did that, we found take a look at the second curve, please. When we did that, we found that the eigen equation crosses the x-axis at multiple points, such as here. So this is the first root, the first eigenvalue, and if we were to go further, there are other further roots as well. However, one interesting thing that we found was that if I was to plot this curve sine lambda n versus lambda n in the imaginary domain, not the real line, but the imaginary line, then we found that in our case, the eigen equation crosses the imaginary axis at one or more points. Okay, this does not happen for common diffusion problems, but for our problem we found under certain conditions, when beta 2 bar is 12, it does not cross the axis. But if beta 2 bar is larger, if it is 18, then it crosses the axis, and I have one eigenvalue which is imaginary in nature. We were able to prove that if that happens, the eigenvalue is pure imaginary. It's not a mixed number. It's not a complex number. It's a purely imaginary number. What is the big deal about it? The big deal about it is that this temperature distribution that I have written here has a exponential of negative lambda squared t term there, which means that if even one of the lambda values are imaginary, then this quantity inside will be positive, and therefore temperature will go to infinity at large times. So we basically were able to conclude from here that whether the cell undergoes thermal runaway or not is predicted by whether there is an imaginary eigenvalue or not. If all the eigenvalues are real, we are safe. If even one of those eigenvalues is imaginary, everything goes for a toss. In Hindi, it's like saying 100 sunar ki or 1 lohar ki, right? All these real eigenvalues work hard, add up to create a solution, a nice happy solution for temperature. And there comes one imaginary eigenvalue and blows up the whole temperature distribution, and my temperature goes to infinity. So in this more complicated problem compared to the previous one, see, in the previous problem the criteria for stability was very simple. In this more complicated problem, what I am saying is that if you want to determine if this problem is stable or not, solve this problem, find out all the eigenvalues of this problem, and verify if all the eigenvalues are real or not. For example, in this case, if beta 2 bar is 12, then we find that all the eigenvalues are real. It does not cross the imaginary axis at all, the blue curve. So at beta 2 bar equals 12, you are safe. But at beta 2 bar equals 18, we find that the line crosses the imaginary axis, and therefore I am no longer safe. So this analysis, long and short of it is, tells me beta 2 equals 12 is okay, beta 2 equals 18 is not okay. Does that make sense? So it's a mathematically convoluted result, but that is because it's a convoluted problem, right? A simpler problem like that one, we were able to derive a simple end result for it. Now we have a more complicated problem, and therefore the result is obviously going to be more complicated. Based on this, the paper, the original paper, has a bunch of analysis. It talks about the different conditions in which thermal runaway will occur or will not occur. So for example, in the beta 1, beta 2 space, if I have two layers, if beta 1 and beta 2 are both negative, the third quadrant, then life is okay, everything converges. But if beta 1 and beta 2 are both large and positive somewhere here, then there is divergence. If beta 1 is negative, but beta 2 is large, then also there will be convergence. It's like two brothers, an evil brother and a good brother, right? The good brother is trying to converge the problem, but if the other brother is sufficiently evil, then the overall house will be destroyed, right? If they are both happy and good, then of course the house will survive. And if they are both very evil, then of course the house will not survive. Yes.
So what is beta I? Beta is the limiting value above which.
No, beta is not the limiting value. Beta is the value. Beta is the rate at which heat generation changes for the first layer and for the second layer. Beta I, the BI. BI is the BO number. Yes. The BO number represents the convective heat transfer coefficient. Yes, absolutely. Right? So a design map like this tells me where I should be. If my beta 1 is 8 and if my beta 2 is also 8, I am doomed. If my beta 2 is, let's say, 4, if my beta 2 is 4, then then the maximum beta 1 that I can tolerate is also about 4. You see what I'm saying? If beta 1 is 12, then I cannot survive. If beta 2 is 12, then no matter what happens, I will diverge. Right? If this brother is sufficiently evil, the second brother cannot save it, no matter how good he or she is. Right? So these kinds of design solutions can be obtained from the work that we had done here. More recently, we have slowly made further and further progress on this problem. I really like stability analysis, so we've continued to work on it. More recently, we've been able to solve this more realistic problem, where I have an array of cylindrical cells arranged inside a rectangular battery pack, which is how it usually happens. Okay, then if each of these cells has a beta and has its own thermal conductivity and so on, and if the pack material, this is the pack material around the cells, and if I tell you the material of the pack around the cell, then the same question, will this battery pack survive or will it undergo thermal runaway? We have been able to derive an analytical criteria to determine the stability of this problem.
Here you are considering the material surrounding it.
Yes, so we are considering the impact of the material surrounding the cell as well. That material could be air, or it could be metal, or it could be whatever else. Okay. The stability criteria for this is even more complicated than the one that I showed just now. So, this entire line of work is a good example of how we start simple and then we grow as time passes. And as a faculty, that does not necessarily happen over one PhD student either, right? The simplest problem was worked on by Krishna, and at that time, even solving that simple problem was a big deal because we did not know, right? And then a bunch of other students, Mohammed and Girish, and now Vinay is the student who's working on this problem. Vinay is from Nepal, and he's a pleasure to talk to. He's very soft, very nice, cool, calm, doesn't lose his calm, very happy to talk to. Each of my students has a character that honestly I miss after they are gone. You know, I miss my students after they're gone. Each of them brings to the table certain strengths, certain weaknesses, and certain quirks in their character, which is very cool to interact with. And even though I am myself growing old, my students remain very young. So we continue to push the envelope on being able to predict the thermal stability of linear systems. The last comment that I would like to make, which may perhaps be relevant to you all, is that the thermal stability problem is not limited to lithium ion cells only. There are other engineering systems in which the heat generation rate is a function of temperature. Whenever the heat generation rate in an engineering system is a function of temperature, there is always likelihood of thermal runaway. I know of at least two systems in which this happens. One is in a MOSFET device. MOSFET is a power electronic transistor or something like that. And what happens in that I don't even know what the symbol is, so let me just call this a MOSFET. Electrical engineer will kill me for this, right? But anyway, the idea in a MOSFET is that a MOSFET operates in constant current conditions. Yeah? And the heat generation rate inside the MOSFET therefore is I square R. R being the electrical resistance, okay? Please don't get confused. Most of the times I'm talking about the thermal resistance being R. Here R means electrical resistance. How does the electrical resistance of most materials change with temperature?
Resistance is a function of rho. Material property.
Yes.
That is a function of
Temperature. Yes. And for many materials, the resistance as a function of temperature goes up. For some materials, they are designed to be insensitive to temperature. But there are some materials, including some MOSFETs, in which the resistance goes up with temperature. And so what will happen here? As this MOSFET generates heat, its resistance will go up. But as its resistance goes up, it starts generating even more heat, because of which its temperature rises even more, because of which it generates even more heat. It is an exact replica of the lithium ion cell problem. Except that there, the increase in temperature was happening because of Arrhenius kinetics. Here, that increase is happening because the resistance increases as a function of temperature. Here also, thermal runaway is known to occur. And these devices, they sort of blow up, boop, all of a sudden because of thermal runaway. So we have some very limited work in trying to understand how that works and what can we do to prevent thermal runaway in MOSFET devices. The other class of devices in which thermal runaway is known to occur is chemical reactors. Chemical reactors are basically large systems in which we mix two chemicals to produce something else, reactions happen, etc., etc. And there also we have the same problem. Suppose I am mixing two materials to produce something else, right? Maybe it's a petroleum plant or God knows what it is, right? Doing some chemical mumbo jumbo. A lot of these reactions are exothermic in nature, right? So when chemical A mixes with chemical B to form chemical C, heat is generated. But we all know that as heat is generated, the temperature will rise, and at a higher temperature, A and B will react even faster, because of which they'll generate more heat, because of which the temperature will rise, because of which they'll generate more heat. Exactly the same story as the lithium ion cell and the MOSFET device. So I am personally aware of at least these three engineering systems in which thermal runaway plays an important role. Where else does thermal runaway occur? I don't know, but I would love to know. Because I believe that the tools that we've developed for lithium ion cells could probably be used for other runaway problems as well. So if you're aware of any problems in which this positive feedback occurs between something and temperature, they both affect each other, please let me know. I'm happy to talk about it. Possibly.
Because there is a motion of neutrons which is directly dependent on the temperature,
Yeah.
that also, if they do not do the cooling, do not supply the coolant, then that will rate of reaction start increasing.
Sure. Yeah. Certainly. Worth looking into. All right. So we'll stop here. We are past our time. We'll take a quick break and we'll start at 4 o'clock for the last tutorial of our day. I know these are long days and the information I'm providing here is very concentrated. I hope you're able to catch something. Please take a deep breath. We're all right, folks. Let's get started. It is the last tutorial of today, and then we will be able to call it a day. So my goal is to continue the discussion, the demonstration of ANSYS. In the previous tutorial, I had merely showed an example problem to show how the flow of information occurs in ANSYS to ultimately tell us what the temperature distribution in a typical body would look like. What I would like to do now is to solve a more realistic problem related to lithium ion batteries. So what we will do is that we will build a 3D geometry of a battery pack containing two cells. Okay, containing two cells, and then we will start heating up those cells, and we want to understand how the temperature in the battery pack changes as a function of time. Okay, so towards that, let me start a new simulation. And let's create the geometry. We'll follow the same process. We'll create the geometry, we'll create a mesh, and then we will specify the properties, the heat generation rate, etc., ask it to solve it, and then we will look at our results. That's the standard process for any numerical simulation. Okay, this is taking a little bit of time. Let's allow it to do what it wants to do. Yeah, so this is the simulation that I did last time. I'm not touching it. I'm starting a new one, a brand new one, which is independent of it. Okay, actually this is not what I want, so let me get out of here and instead use design modeler, in which I will create my geometry. Let's just think of some good numbers here. These cells are 18650 cells, so the diameter of each cell is 18 millimeters. So the size of this battery pack could be 18 plus 18 plus 18, maybe about 50 millimeters or so. Okay, so I'm going to go and change the units to millimeters, and I'm going to start sketching first the base of my battery pack. Let me give it some dimensions. We agreed on 50 by 50. So I'll say 50 millimeters. Is this visible in the back? If not, please don't hesitate to come forward. Let me also align this with this. Good. Alright, so here is my 50 by 50 base. I'm going to extrude it. Hopefully this looks familiar from the work that we did yesterday. And the cells are 65 millimeters tall. Okay, so I will extrude it to 65 millimeters. And this is my base. This is my battery pack, right? I have to build 2 holes in it in order to insert my cells. So let's do that. For that, I would like to create a new plane first. From this face, sure, and on plane 4, I will create a sketch for 2 circles. (18) and 18, yeah, and then I also want to sort of place them in the center. So this, I'll say distance between the center and this needs to be 25, and similarly the distance, will they fit? Yes, they should fit. This also needs to be 25. So I put them in the center. I also want to make sure that they're equally spaced. So this to this is, say, 5 millimeters. No, it needs to be 9, it needs to be more than 9, right? So let me call it 12 millimeters. So let's just do a simple asymmetry. This cell is very close to the boundary, and this cell we will push away from the boundary. I just want to be able to capture that effect here. So this versus this, from this distance is more than 12. It is, say, 18. You see what I'm saying? I'm trying to create a little bit of an asymmetry to see how it will affect my thermal performance. So let's go ahead and then take this sketch and create, extrude, slice material all the way to 65 millimeters, and I have now created my geometry that contains 3 solids. One is this base, correct? The second is this cell, and the third is that other cell. This cell, this cell, this cell, and the rest. Got it? Let me combine these into a single part, and I'm ready to move forward. Okay, I'm done with my geometry. Part A of the problem is done. I can always come back and change things around here, right? That's one of the advantages of numerical simulations. I can always come back. Somebody says, oh, can you push the cells closer to the boundary or away from the boundary, or can you change the size of the cells or the geometry or whatever? It's easy to come back here and make those changes. There is a small clearance between the 2 cells. At the top and bottom, no. Usually there is no clearance at the top and bottom.
Cell and the back bottom.
This clearance?
We are having a cuboid.
Yes.
And
I see what you're saying. No, typically the cells are very tightly packed in that clearance, and therefore it is very tight. So we'll ignore that for now. Okay. I know it's not going to be zero, and that effect can be accounted for if you really wish. For now, let's neglect that. Okay. All right. So I'm done with this here. I can close this, and I can go and mesh it. Last time I meshed it automatically. Today let me show you a few features of meshing, because the mesh last time was very unsatisfactory. It was too coarse. So let's open the meshing and have a little bit of control over how fine my mesh should be. So let's wait for the meshing to open. Usually meshing is the one that takes the most time. It takes a lot of time for the software to discretize the body into number of nodes and assign the locations of each node and so on. Okay. Oh, thank God. For a moment I thought it wasn't there. So what I can always do is start with generating the default mesh. The default mesh, as you can see, is not great. You know, the number of elements here, if I go down here and look, is only a few thousand, which is very, very poor. I can go up to 100,000 and it will still compute very quickly. So what I will do here is that I will change the default element size from 4e minus 3 to maybe 2e minus 3 and run this again. And you can see that my mesh has become better. I'll do this, I'll make it a little finer, and now it's taking time to mesh because the number of elements is now going up. Now I think I'm much happier with this mesh than I was with the previous mesh. Even this does not have a lot of elements. It has only 200,000 elements, which is okay. You know, I could go more. For the purposes of this demonstration, because I want to compute within a reasonable time, I will actually go back to 0.002. See, there is the trade-off between accuracy and computational cost. If I really wanted accuracy, I would have gone down even more. But because right now in this lecture, computational time is important for me, I want to demonstrate a lot of concepts in the limited time. So allow me to go coarser so that the calculations will happen a little faster. So let's live with this mesh. Okay. All right. So I'll close here and I'm ready to, let me update the project so that I can go to the setup and start defining the materials and so on and so forth. There really is not much of a difference. Both of them solve roughly the same equations in roughly the same manner. So it all boils down to what you're more familiar with. I'm somehow more familiar with CFX. That's the only reason. In some way, in fact, Fluent is a more sophisticated, comprehensive tool. CFX is a little more basic. So what do we have to do here? We have to tell it what the materials are. We have to tell it what the boundary conditions are. We have to tell it how much heat is being generated in each cell, right? And since this is a transient simulation, we have to tell it how long to go in time in order to find the temperature field, okay? So let's remember to do each one of that when this new window opens. One by one, we will define the materials, the two materials, cell and pack. We will assign them to them. We will put a number for heat generation rate, the convective heat transfer coefficient, and I think that is about it. So to begin with, let me go to materials. Remember that this had only a few materials available. So I am going to insert a new material and I will call it cell or cell material, cell mat. I will tell that this is a solid and I will specify its properties. Its density is about 2200 kg per meter cube. These are based on my own understanding of these numbers. The thermal conductivity We all know that the thermal conductivity of the cell is highly anisotropic. There is a way, by default it only accepts isotropic thermal conductivity. There is a hack around this GUI that you can use to specify anisotropic thermal conductivity. Okay, takes a little bit of time, so I'm not going to do that. Alright, so keep in mind that I'm doing a bit of an approximation in the interest of time. I will just assume the cell to have a single valued thermal conductivity of 0.5 watt per meter Kelvin. Okay. And then I will define another material called pack mat, which is also a solid. The pack material is typically metal. It has higher density and thermal conductivity. So maybe we can assume values, that are representative of metals. The thermal conductivity will be higher. So let's assume a value of 10 watt per meter Kelvin or so. Steel, different types of steels typically have thermal conductivity of that order. If it was aluminum, it would be even larger. Let me just for now assume values corresponding to steel. So let me OK out of here. Let me rename this as cell. So this cell is a solid and it is this and this. These two are cells. Okay. No, I will just select only one of them and I will assign it cell mat, and I will get out of here for a little bit. I want to rename this as cell 1. I want to define cell 1 and cell 2 separately. So this is cell 1. Let me similarly define cell 2. Which would be this one. It's a solid, it is cell mat. And then the third material here is the pack, which is the rest of it, and that is made up of pack mat. So I hope you can see that the software tool has been designed to be friendly to us, right? It's once you learn the basics of what is where, it's very easy to click and assign properties and do this, do that. There is no programming needed for this. There is no coding needed, right? Everything is nice and friendly. That is why it becomes easy for anybody to do numerical simulations. Alright, so then there is going to be heat generation in this body. So I need to go to cell 1 and I need to insert a subdomain, and I'll call it cell 1 heat, and this is the entire cell itself, and in this there is a heat source, a total heat source of certain number of watts, right? So let's just say 50 watts of heat occurs here, or a better way of doing this is, I'll call it cell 1 heat gen, and I will define the meaning of cell 1 heat gen here. Cell 1 heat gen, this is equal to 50 watts. Okay, so it understands what the meaning of cell 1 heat gen is. Cell 1 heat gen is 50 watts. While I'm here, I can also define cell 2 heat gen, and that would also be, why not call it both 50 watts. 50 watts is a rather large number, I think, but we'll see what happens. Okay, so just like I defined cell 1 heat, let me insert a subdomain called cell 2 heat, and that would be all of this, and it would have a source called cell 2 heat gen. I'm continuously looking at this because if there's any error, spelling mistakes, etc., an error would pop up there. But so far I think everything is good. The last thing we need to do is to specify cooling. So in the pack material, I will insert a boundary. I will say the cooling boundary, which would be pretty much all the walls. 1, 2, 3, 4, 5, 6. On all of them, I will apply a heat transfer coefficient. I will call it H cool. And the outside temperature can be just 0 Kelvin. Again, remember I said last time, 0 Kelvin does not literally mean 0 Kelvin. When I say 0 Kelvin, I'm simply saying room temperature, ambient temperature, so that any other temperature that I find after my calculations are over is relative to ambient temperature. So if my simulation after all of this says that the temperature here is 10 Kelvin, it really means that the temperature there is 10 Kelvin above room temperature. Okay? Alright, so here we are. It threw up an error saying I don't know what H cool means, which is okay. I will define H cool to be 20 watt per meter square per Kelvin and oh good, it accepted it, so everything is good. We are ready to go. I do need to specify to the solver that I am interested in carrying out a transient simulation, and as soon as I say transient, it says how long do you want the simulation to run. So, and I will say how about we run it for 2000 seconds. Then it asks how many time steps do you want to take, what should be the time step, and here let me just choose 20 seconds time steps. So total of 100 time steps it will take, and initially the time is 0. Okay, and obviously if I am running a transient simulation, then I must specify the initial temperature. So the initial temperature everywhere is 0 Kelvin, room temperature. Okay, so I start with room temperature. These two cells will begin to generate heat, and I'm now going to understand how the temperature changes as a function of time. Under the solver control, just like last time, I'm going to tighten this a little bit, and I will also inside this I will say please save my results at each time step, and I will insert a temperature sensor inside. I will say expression, and I will say max val of temperature at cell 1. So this basically means please monitor the maximum value of temperature anywhere inside cell 1 and keep reporting it to me. Okay. And I can also define one more similarly. That would be monitor point 2. It would be max val of temperature at cell 2. If I wanted to place a temperature sensor at a specific location, I could do that too. Probe, exactly. I could place a probe anywhere I want and it would monitor the temperature there. But really I'm interested in the maximum temperature, and therefore I can define it this way. Okay, let's take a deep breath and make sure that we have defined everything we needed. Initial temperature has been defined. I think life is okay.
How do you define cell material and the properties
The cell material and the properties were defined here, cell mat.
using blank material?
Using what?
Using a blank material and you are specifying.
I put in my own numbers. I inserted my own numbers. And as I was saying, there is an error here in the sense that for the cell material, I'm specifying the thermal conductivity to be 0.5, whereas I know that it is anisotropic, right? There is a way to bypass this and specify anisotropic properties. Takes a little bit of time. You have to write a separate script for it. So let me skip that in the interest of time, okay? Alright, I think we are ready to go. By the way, the fact that you referred about the clearance between the cell and the pack, that there may be some contact resistance at that point, could be accounted for here. So by default, the solid to solid interface is defined based on perfect thermal contact between the two. But if you wish, you can come here and you can define a thermal contact resistance, or you can define that there is a thin material of air or epoxy of a certain thickness at that point. Okay, so if there is a contact resistance, it can be accounted for here. I'm not going to do that, and I'm just going to get out of here. Okay, any other questions or comments? The chemistry of the cell is not accounted for here explicitly. We have defined the heat generation rate to be 50 watts. So I am assuming that whatever chemistry is happening in the cell, I already know that it generates a constant 50 watts of heat. If the heat generation rate is a function of temperature, then I can model that as well. Okay, let me run this case first and let's look at the results. Then we will come back and change this 50 watts to be a function of temperature. Okay, then if we change it to a function of temperature, we will see the cell getting into thermal runaway under certain conditions. Okay, any other questions or comments? All right, so let's go out of here. And see, numerical simulations are easy in the sense that having set all this up, now you can start asking questions. What happens if the cell has a different diameter? What happens if the conductivity is different or the heat transfer coefficient is different? You can always come back here, change it and run your simulation again. Okay? And oftentimes if the geometry is complicated enough and if we are not able to derive an exact solution for it like we have done for simple geometries, then numerical simulations is your only option. Alright, so let's finish this here and I'm ready to run this. I suspect that this simulation will also not take a long time to run, not more than a minute or so, perhaps even less. This is where it is setting up those equations, creating the matrix, doing the matrix inversion sometime now, and solving for temperature. These are my user points. The two cells have roughly the same temperature. One of them is slightly hotter because it was farther away from the heating boundary. You know, if it had been completely symmetric, these two curves would have been exactly identical to each other. And as you can see, it rises very fast to begin with and it slowly stabilizes. The temperature rises very high, right? The cell will not survive. 50 watts was too much of heat, I think. At this point, 200 degrees C temperature rise, the cell will blow up. So we already know, if somebody says, I want a cell that produces 50 watts of heating, not going to work. Not possible. You probably have to increase the value of H, cool it more aggressively in order to bring down the temperature, right? Using this simulation framework, you can ask all these questions. What is the minimum H needed to be able to accommodate a 50 watt cell? Can I switch off one of the cells and only run one of them at a time? Will that help me reduce the temperature, and so on? My heat generation rate was defined to be constant 50 watts. I can define it in other creative ways. I can say it is 50 watts for the first 30 seconds, and then it goes down to 10 watts, and then after 30 more seconds it comes up to 50 watts. So you're giving a small break to the cell in order to allow it to cool down a little bit, right? Will that allow you to keep the temperature within acceptable limits or not? Right? You can even say, if the cell temperature exceeds a certain value, shut it down completely for a certain amount of time. Right? These are all strategies that you would probably use in real life, and those can all be simulated in a setting like this. So we had specified 100 iterations, 100 steps, time steps. We are done with about 70 of them. So very soon it will finish up. Okay. And at that time it will say simulation done. We will be able to close this and open the results window. So let's look at the contour, all the domains, everywhere, and this is how the temperature field looks like at the final time. Okay, it's a little difficult to understand what in the world is going on here. So what I can do is to create a new location called a plane, a new plane location. This plane would be where is this plane? (65), half of 65 is 32.5, so 0.0325 should put us at the center. Does it? Yes. So on the contour I can go and say plot my temperature only in that plane, so that I can see a that's how the temperature looks like. This cell is slightly, not much, slightly cooler than the other one, simply because this is slightly closer to the cooling boundary. Not a big difference. So if your battery engineer asks you, should I place it this far or this far from the cooling boundary, your answer is yeah, doesn't matter, do whatever you want, right? It's not a major effect. Clearly your battery engineer is also juggling 5 other constraints, so he or she will be happy to hear you say it doesn't matter. Alright, I can also, by the way, look at this as a function of time. This is only the temperature at the final time. Initially everything is cold, of course, right? And then as time passes, you can see the heat is being generated inside, and slowly it begins to diffuse outwards, and things get hotter and hotter as time passes. Right? You can literally see the wave traveling outwards as time passes. I think you can actually create an animation. Yeah, so this is how the temperature changes as a function of time. The temperature is rising, but it eventually reaches a steady state. I'm not worried, even though the temperature is very large, and we can fix that by changing the heat generation rate, it will not go to infinity. It will eventually stabilize. Okay, let's stop this here, and let's go back, and as I had suggested, consider a scenario in which the heat generation rate becomes a function of temperature in one of the two cells. Meaning that one of the cells has gone rogue, and the heat generation in the cell will increase as a function of temperature. Let's see what will happen in a scenario like that. So I will say cell to heat gen. Let me just actually turn this into a very small number, and cell 1 heat generation, instead of 5 watts, I will say beta times temperature. Okay, it will not know what beta is, so I will insert beta. Okay, so it uses beta. Oops, it uses beta for something else. So let me sorry, I think pushed it too hard and moved it. Thank you. So I will rename it to, sorry, I will change this to and I will define this to, I need a value for beta. It should be a small number, I think. Let's just call it 2 watt per Kelvin. I hope that works. It does. So basically we are now saying that the heat generation rate is equal to 2 times the local temperature inside cell 1. Okay. In fact, I think this 2 number is extremely large. Let me make it 0.1 perhaps. Let's see. If thermal runaway doesn't happen, then we'll come back and increase this number. We'll kill the cell, I promise. One way or the other. Okay? Alright. So in the interest of time, let me make my number of steps slightly larger. So instead of 20, I'll have 50. So that I have only 40 steps. Simulation will happen faster. Okay? Oh, and the initial temperature, let me make it slightly hotter. So this is initially about 20 Kelvin hotter than the ambient. So it is slightly warm to begin with, and let's see what happens as time passes. So this is ready to go, I think. I'm going to say clear generated data and just start from scratch. A user-friendly tool like this is actually almost addictive, right? Once you set it up, you can come up with all kinds of questions to ask. What if I do this? What if I do that? What if the cell thermal conductivity can change, or the cooling can change, or the material can change, or what have you? This should take 40 time steps. See, immediately you can see that the temperatures of the two cells are now very different. Cell 1 has a higher temperature, but it is not showing the going to infinity type of behavior yet. Will it? Will it not? I don't know. I think that beta number needs to, 0.1 was too less, I think. So let's go back and push the cell a little more. Instead of 0.1 value for beta, let's make this 1. Yeah, I think that will kill the cell. Or maybe I should have made it 2. We'll see. Clear generated data. Alright, let's see what happens now. Yeah, see, that one took off right away. Earlier it was converging, now it is diverging. And even the innocent cell, which was really not generating much heat by itself, gets captured, gets caught in the crossfire, and it also undergoes thermal runaway. It's also doing the same thing, it's just doing it slower, right? You can see, it's not the actual numbers that is important. What is more important is the nature of the curve. Earlier it was like this, now it is like this. And the numbers you can see here are hopelessly large. See how sensitive that beta was. We made it from 0.1 to 1, and somewhere in between is the threshold beyond which this behavior happens. If you have the time, you can try it a few different values and you can get closer to the value at which this transition occurs. It is somewhere between 0.1 and 1.0. You know what I'm saying? I just want to let this finish so that we can look at the results and visualize what is going on as well. Once it gets caught in this positive feedback, there is no going back, right? That's sort of the beauty of this thing. More heat generation, more temperature rise, therefore more heat generation, therefore more temperature rise, and it's like a chakra view that it cannot get out of. It's doomed to fail. And not only did the first cell fail, but the second one also failed as a result of that. It failed a little later, and it failed a little less spectacularly, but nevertheless it failed, right? Let's go to the results window and see how this would look like in terms of the temperature field in the body. Any questions while this loads? The capabilities enabled by the simulation tools like CFX really make it possible for all of us to become creative. At the end of the day, the kind of math that I have presented has its own limitations. It can only work for certain specific simplified problems, right? You go out in the real world and try to solve real world problems. Those mathematical results can guide your direction to go, right? But the exact analysis will probably boil down to numerical simulations like this. Okay? So let's open CFX post. Students like Mohammed Parizi from my lab, for example, did a lot of math in my lab. Now when he works for Tesla, I think he runs simulations all day. Okay, so I will see, one of the cells dies, the other one in which there was no heat generation. It's still very hot, by the way. It's not zero, it's extremely hot. In fact, let's run this as a video. To see how the temperature will change. For a long while, not much is happening. But towards the end, the whole thing explodes. This is a little difficult to understand because of the large temperature range. Even though it was blue for the most time, it was actually quite bad. You see what I'm saying? Let me see if I can. Will this help? It's very cold here. It remains cold. But the point is that it is still rising all the time. Sorry, I'm not able to capture the exact effect in order to visualize, but the time plot, yeah, this only shows up here because of the dramatic range. It only shows up in the end. But anyway, if you see the temperature curve, temperature versus time curve that we had shown, it was very clear that both of those cells are going to undergo thermal runaway. In fact, this is a very large range, right? If I was to reduce that range, you will already see that you saw that at early times that it was sort of going there, and then at some point it just took off and the entire thing exploded. This is pretty much an explosion, right? It doesn't look very dramatic, but it is an explosion, and it is because of the large value of beta in our calculations. I can go and ask myself all kinds of questions now. What is the minimum value of beta at which this will not happen? How do I change the thermal conductivity? What happens if I change the packed material, right? The packed material had a thermal conductivity of only 10. What if it was 200? What if the cell had better thermal conductivity? And so on, right? Let's just run one more calculation at a somewhat better value of beta. We know that at 0.1 things were good, and at 1 things blew up. What number should we choose? I still wanted to blow up, but not as badly. 0.5? Yeah? Any other thoughts? We can only guess here, honestly. So, yeah, sure, 0.5. I have a feeling that it will still explode at 0.5. So, clear generated data. Yeah, run from initial conditions, and there you go. Our calculations have started. This is probably the last calculation we'll do today. Let's see how it works out. It tends to be going like this, but the green curve is going upwards, right? The red curve seems to want to reach a steady state, but at some point it will get the message and it will begin to curve up instead of going like this. See, at about this point, it has changed its shape from concave to convex, right? The evil brother has spoiled the good brother. Yeah, there's so much heat being generated in the other one that it's passing on some of its heat to the other, the good brother, and now they are both going to explode. Yep, it's done. It's gone. Even at 0.5, it goes. If you really want, we can try 0.2 and see how that looks. Why not? We'll just stop this. We know how it's going to look. Let's just go back and try if this works. आपका मैजिक आप वो बोलते हैं ना, आपके हाथ में तो जादू है. Thank you. It just needs to last 2 more minutes, I think. So we will go back here. What number should we choose now? You've done 0.1, 1, 0.5, it fails. So, point what? 0.2, 0.3? How about 0.25? Okay, let's do 0.25. Any guesses on whether it will survive at 0.25 or not? How many of you say the good brother will survive? See, the thing is, we have proved this mathematically. Either both of them will survive or both of them will not survive. It cannot be that one of them survives, the other one doesn't survive, because the one that does not survive will eventually generate enough heat to kill the good one. So either they both survive or they both do not survive, and I am open to bets about what will happen in this case. Did I hit apply? Okay. Alright, they both seem to be doing okay. Even the green one, but now it seems to be, the green one seems to be going the other way, the diverging way. Whereas the red one still wants to survive. The green one is clearly gone, and therefore eventually it will kill the red one as well. So far the red one is doing okay. This shows, the fact that it's taking a long time shows that we are very close to the threshold. At the threshold, add one more drop of beta and the thing explodes. So 0.25 is pretty darn close to the threshold. And you can see, I can sort of feel now that it has changed shape. It was going concave and now it is starting to go convex. You give it a little more time and it will start rising rapidly as well. Well, we are at the end of the simulation time, so we could not quite see that. But I think it is quite clear that the green one is going to diverge, and ultimately, if you give it enough time, the red one will diverge as well. So the threshold is somewhere between 0.2 and 2.5. Yes, between 0.1 and 0.25. Okay? You give it a few more trials and you will get to, it's like the Newton-Raphson method, right? You're getting closer and closer to the root. Few more iterations, you will know exactly the threshold. And honestly, come to think of it, finding the threshold in this manner is not easy, it is cumbersome. The mathematical tools that we have defined gave us a simple equation with which we could exactly derive the stability criteria. The only disadvantage there was that it was valid only for specific simple geometries. It cannot quite possibly do what we are doing here. Okay? Alright, so we are at 5 o'clock, so perhaps we can stop here. Thanks again for a good day. I'll see you all fresh and early tomorrow at 9 o'clock, and we'll talk about some more interesting stuff related to heat transfer in batteries.